Hello everyone, good morning.
Good morning, sir. Sir, I will request you to please check, like I have given you the privilege to be a presenter. So I request you to please check whether you are able to share the screen.
Sure. I hope you are able to see my screen.
Yes, sir. A very good afternoon to all the participants. A very good morning to all the participants. Good morning to Puneet sir and Ritesh sir, and to all our coordinator. Today we are having quiz. All the details are already uploaded in the drive. I request you all to please visit the drive link. There, all the details are provided. So please maintain please go through the instruction and please read it carefully. All the details will be given there. So, Ritesh sir, should we start with the session or should we wait for another 5 minutes? What you suggest?
We can wait for another couple of minutes.
Okay, sure. Thank you, sir.
I think we can start now.
So, sir, we can start.
Sure.
Yeah. Okay. Thank you, Ritesh, sir.
Uh, Good morning, all. So, I hope you all are staying safe. So, this is day 7 for the workshop, and we so today I'm going to talk about Intel SoC FPGA Embedded Development Suite, that is SoC EDS. I'll be giving you a quick recap of the architecture, which uh, Vikas had explained detail about the SoC architecture and also the day 2, and then going forward. I'll be taking up SoC EDS, yes, and then details about what all tools are provided, how to compile the code, how to debug the code, and then how to test the code on the hardware. And the lab also will walk through all the lab material and how to get hands-on on the D1 SoC board. So let's get started now. Yeah. So a quick recap about the SoC architecture. It's the Intel FPGA SoC architecture. Uh, here we have there are two parts, or you can say mainly the SoC is divided into two parts. The SoC name itself suggests that it contains a hard processor and FPGA. So the details of the SoC FPGAs are like it has the blue portion you can see here. There are two ARM core A9 with a floating point unit and L1 cache. Then L2 cache is shared by the both processors, and we have set of peripherals available for accessing GPIO, SPI, and many kinds of memories like flash memories and DDR memories. And then we have FPGA, which we call it as fabric, or you can say the LUT structures, and the reprogrammability is possible because of the FPGA. So this is shown in the green color. So we have 8 input ALMs, and then we multiples of variable precision DSPs, M10K memory blocks, and FPLLs for clocking. So these are all part of the FPGA fabric, and you'll see this is the similar architecture you can find in the FPGAs, different families of the FPGA too. So and then along with the FPGA, we have a hard multi-port DDR and hard PCIe plus few trans receivers where you can actually have a high-speed serial I/O connected to these trans receivers. So this gives a packed bundle of uh, multi-utility processing unit. Like you have a CPU where you can actually develop your algorithms or code which are routinely executed, while on the FPGA you develop accelerator function, for example, or you do a function which needs parallelism and pipelinism, and that can be well implemented in FPGAs. So, taking both the advantages, you can there is a plethora of applications that can be built on top of this kind of SoCs. Now, moving to next is we also touched upon the configuration part because had spoken about this in the previous slide, so just wanted to catch up on those uh, and touch upon those parts. We what are different FPGA configuration and CPU boot options available. So on the left hand side, you'll see we have FPGA configuration sources like starting from passive parallel, passive serial, and then flash memory QSPI, and then PCIe, where you can actually say, suppose this is a card, this FPGA is on top of the card, and then uh, the FPGA can be configured through the host processor. While on the right hand side, you'll see for HPS, the boot sources are multiple flash devices. With this, the designer gets a lot of flexibility whether he wants to put from FPGA or from HPS. So uh, either either the boot also boot can be stored in the FPGA ROM and then can be loaded from FPGA to HPS, or the otherwise the binaries of the FPGA can be stored in the flash memory, and HPS can read it and configure it. So the flexibility is there in this. Uh, And of course, as you know, general FPGA, like traditional FPGAs, we have a JTAG port that also can be configured. So today in lab, we'll be seeing how to configure the JTAG. The reason I'm touching this section here is because this might be this might be a starting point where, okay, I have a board, and what next? How do I execute my binaries? How do I start loading my FPGA, or how do I boot my ARM core? So for more details of that particular board, now this is more specific to the FPGA itself, or the SoC device itself. But say every board has its own technique to boot the CPU and load the FPGA binaries. So there might be switches, or in few cases, few of the boards, there might be the configuration process might be. You should look out for the user guide of that board to understand what type of configuration that board supports. So we'll now deep dive into a little bit of the architecture, because I think that before we put our hands into code, we need to really understand what exactly the SoC architecture is, to get best use of that architecture, basically. Like because if you are a software developer or you're a device driver developer, and you're using this device for computation, uh, the only uh, uh, the only thing which you can get high performance out of this device is understanding the architecture in detail. So let's see what are different architecture options, or what are the features the SoC architecture provides us. So this is a high level block diagram uh, of the FPGA SoC, Cyclone 5 SoC, for example. Now that is dual core processors with shared 512 KB L2 cache, and high bandwidth interface between SoC and FPGA and memory controller. So that's shown here. So this part, that's high bandwidth interfaces are there, and of course the FPGA to HD RAM interfaces. Then we have ACP, that is acceleration coherent port, and that is also one of the feature used for coherency. We'll discuss in upcoming slides about that. And of course, SCU, that also we'll touch upon later, right? And next is like we discussed, there are configuration controller where you can actually configure from HPS to FPGA. While on the left-hand side, you'll see these are the high-speed interfaces. Yeah, so that's a EMAC, that is Ethernet MAC. So we have triple speed Ethernet, that is 10 bar, 100 bar, 1000 Mbps speed, supported for this FPGA. While you also have USB OTG, and then there are two numbers of that controller, and then flash controller DMA, that is direct memory access, and others are trace control and debug ports. So uh, yeah, so these are the high speed interfaces, while on the left hand side you'll see low speed peripherals supported like timer, GPIO, UART. So a typical microprocessor peripherals, which you would like to have it to write your code. Moving next, system throughput. As a designer, as a software engineer, wanted to take full advantage of this SOC, you would also want to know what is the system throughput this SOC supports. Like for example, in Cyclone 5 SOC, we have 9.6 Gbps of maximum throughput because okay, so this 9.6 Gbps is for 32-bit read and write, and that is lightweight interface. While for high bandwidth, dedicated interface, which is on your right hand side, this 128-bit read and write, that supports up to 38.4 Gbps. Now, this bandwidth is good enough for doing a memory transfer or bulk data transfer from HPS part to FPGA or FPGA to HPS part. Now, the reason of having 38.4 Gbps is, say, 128-bit width the database is, and it's clocking at 150 megahertz. Since we have read and write separate interfaces, uh, that's why we can actually get double the throughput. It's like 128 plus 128 into 150 megahertz, right? So yeah, and then similar, it's where we have throughput for ARIA 5 SoC also. Or moving next, the coherent memory sharing. So this is one of the feature which SoC device provides for coherent cache or accessing coherency. Now, coherency is very important for a heterogeneous computing, where I see this SoC as a heterogeneous device because, of course, it has a HPS, that's the ARM core, and the FPGA. So, say you want to build a accelerator function in your FPGA, so and you want to have a coherency with your CPU. So this SoC provides that feature. Now, uh, let us step back and say what does coherency mean? And that's what I want to give an analogy. Say, okay, so what does the coherency mean in this context? So, for instance, you have a laptop and say uh, you get a problem or a issue with Microsoft Office, and you need a support to you need someone to look into this issue. So you call the customer service and say, okay, hey, my Microsoft Office is broken. Can you help? So the support guy says there are two options. Either I will tell the steps and you fix it, or give me control of your system and I will fix it. So the advantage of the later part, that is option two, is there is no delay or lag, or the both the person, like the support person and the person who is near laptop, is really not in sync, or they both actually can access the same machine together, since the support guy is able to do a remote access. So that's the analogy of the coherency. So suppose an accelerator, which is a master function, wants to access the memory of CPU because the accelerator function wants to have a sync of memory between the CPU and the accelerator. So that is where coherency comes into picture. And if the entire subsystem supports coherency, you can actually have the both memories in sync and they're not in out of order. So basically, so if there is any change in the cache memory, that can be seen from an outside accelerator, and that can update any value outside the accelerator. Uh, so Cyclone 5 SoCs provide coherencies, and this is one-way coherency. Basically, one-way coherency allows an external ACP master. Now, ACP master is your FPGA accelerator, for example, to see the coherent memory of Cortex A9 or ARM core. But then it doesn't allow the vice versa. It doesn't allow the ARM core to see what's happening in the FPGA memory. So that's a one-way coherency. So Cyclone 5 SoCs support one-way coherency. And the ACP mapper, which is shown here, that plays a key part here. And ACP, it can support up to 8 transactions in flight and unlimited transactions pending. So moving next, memory protection. Yeah, so this is another important feature of the ARM subsystem in the SoC. That's support for ECC. So error correcting code. So basically ECC in this case supports single bit error correction and double bit error detection. And there are DDR controllers, L2 cache, on-chip memories, and flash memories, DMA, USB, and all other peripherals like USB, Ethernet, MAC, and CAN. They're all supported by ECC. So that means the data coming into the SoC subsystem is made sure that the data is really stable and you don't have an issue with that. So, like a typical example of bit flip issues, which are typically seen in a high-speed memory devices. So those can be avoided with this kind of applications. So this brings a robust implementation in our software because you don't expect any data mismatch or any data corruption in your memory. Now, here, just I want to touch upon few things here, like L3 slave peripheral switch is okay. Let's start with the switch matrix. We have L3 main switch, and which actually controls your high-speed bridges like FPGA to HPS bridge and HPS to FPGA bridge, while the L3's slave peripheral switch actually supports or controls your 32-bit AXI bus, which is lightweight HPS to FPGA bridge. While your these two bridges are actually configurable, that is 32, 64, and 128-bit configurable. So moving next to the HPS DDR controller, because we have seen in the first slide, we have DDR memory controller dedicated in HPS. So that brings that also gives you a lot of flexibility. The reason is it has two types of controller, that is single port controller and multi-port front-end controller. So what does mean is actually your your MPU, that is microprocessor unit, as ARM core, can actually access the DDR, as well as your FPGA also can access the DDR. Now that brings in more flexibility because you can actually FPGA when is implementing as an accelerator or as and any function it wants to implement, it can still use the same memory, shared memory, which is controlled or accessed by the processor subsystem. And this is a little more details of how it is done on the FPGA to SPS SDRAM port utilization. So like these are different types of bus protocols supported by your multi-port controller or the multi-port SDA controller. So basically, there are different types of port configurations. That's up to 4 read ports, 4 write ports, and 6 command ports. Now, any transaction, any protocol, like for example, you have AXI 64-bit or 28 I'm sorry, 28-bit AXI. Those can be implemented using a few combinations of your command read and write. For instance, in this case, 64-bit AXI can be implemented using 2 command, 1 read, and 1 write. So like that, so you can mix and match different protocols on the same bus using this multi-port interface. DDR memory controller, again, this is more a little detail of the SDRAM controller, which is hardened inside. So it provides relative port priority. Now, this is something when you have a complex logic going into the FPGA, and which requires off-chip memory. Off-chip memory is your DDR3, for example. Now, there might be multiple interfaces which are trying to access those a single memory. So you'll always need to prioritize which of your module requires more access and which of your module can actually be a little slower. So that is defined by the priority, and most of like the this mic SDRAM controller supports multiple varieties of priorities, like say relative port priority, which is deficit weighted round robin, or it also supports absolute priority, like, which is multi-level. Like for example, okay, of course we'll be discussing in the next slide, so we'll take it later. Priority bypass, that also is there in the next slide. So ECC, again, as we discussed previously, so the DDR supports 16-bit, 32-bit ECC against error correction up to single bit and detection up to 2 bits. Bank management, command reordering, power management. So all these are the features. Uh, and trust zone security is one of the proprietary features from ARM, while it is a security feature provided by ARM subsystem where you actually can make sure that at application level your uh, your design is not accessing particular section of the memory. This is for security purpose, and these are in the you can define the touchstone securities in the boundaries of 1 MB data space. Then the DDI memory controller also provides exclusive memory sharing and memory protection. Now, yeah, so memory protection, again, memory protection in that you have a trust zone security as a a sub option or a sub feature. So as we discussed in previous slide, we'll talk about multi-port scheduling. That's a priority, how you prioritize your access on the multi-port subsystem. So in say suppose okay, you have multiple master interfaces which wants to access FPJ, or okay, there are master interfaces in the FPJ and wants to access DDR which is sitting on the DDR controller in the HPS part. So always that can be there can be a contention, like who wants to access what type of uh, like which port wants to access the memory at what time. So there can be the two types of priorities. That is, one is absolute priority and relative priority. So in absolute priority, you can actually say, okay, my port A wants to access, has to have a higher priority, and whenever there is any transaction happening on that port, this DDR controller serves as quickly as possible. So it halts all other transactions and it gives the priority to it. So highest priority port transaction always serve first. So next is absolute priority can be changed dynamically, and it can be assigned to any FPGA dynamically. Now this is done. You can see the diagram here. So you can see the priority, absolute priority here given 7, 6, 5, 4, 3, 2, 1, 0. So any critical module which needs the memory access has to be given highest priority, which is 7, and is to the CPU. And then in the relative priority, you can actually have multiple ports assigning to the same priority level. Now, in that case, there will be a round robin scheduling, and based on round robin is like, say, suppose there are two A and B ports, or I would say port 1 and L3 switch, both are trying to access, say, and then one transaction is served for port 1, for example, and the next transaction is served for L3 switch, and so on and so forth. It keeps on repeating. So next is memory protection for shared memory. Yeah, so this is we touched upon in previous slide that we have uh, Like for example, there is an IP which is accessing the DDR memory, which is attached to the DDR controller, and you are trying to access this FPGA IP space, and this is what it is dedicated that you are supposed to only access this. Uh, then, but then you don't want this IP to access the IO the OS space, because if there is any data getting corrupted on the OS memory space, that means your image gets uh, corrupted and your boot fails. So you don't want to actually touch those space. So you can actually add protection rules here to in the DDR controller saying you don't want this IP to access this part of the memory, for example. And there are more than 20, like there are like 20 rules supported here with different rules, and one of them, as I discussed, is the uh, trust zone security transaction, and that is the proprietary from ARM. Now, Cyclone 5 and Area 5. Okay, let's move to the next important topic, which is HPS physical memory mapping. Now, you this is a very important point here to understand how do you look a memory from different angles or different subsystems. This SoC itself is a complex device. You have multiple masters accessing a single memory. Then the important question for a developer, a software developer, or a FPGA hardware developer is to understand how do I see to my memory, or from how do I really uh, map my logic to this single memory which is available to me. So uh, the answer is to have physical memory map and define the address. So address spaces are divided into one or more non-overlapping regions. For example, the MPU address space has peripherals, FPGA slaves, SDRAM window, and boot region, which is on the middle part. So here, and next the like for example L3. On the L3 we have ACP window. Now this ACP window wants to, okay, what does the window means? Now the window region actually provides access to other address space. So that's the concept of the windowing. So that means your L3 peripherals can actually see through the ACP window this part of the region, because you have mapped this window to this particular region. Now, by default, it is mapped to 00, but of course, you can actually, in this MPU's region, actually SDRAM region can be actually reduced, increased or reduced, and the window size also can be increased or reduced. So typically in this case, the ACP window is seeing the entire 1 GB space, 0 to 1 GB. So any L3 peripheral can actually view this region through ACP window. And also the SDRAM window, the MPU region space can grow and shrink. As I said, it can actually shrink down or also it can increase down. But then the problem is you are giving up on the boot regions and the HPC to FPGA slave uh, memory map regions. So again, these are the different techniques, and depends on and it totally depends on your application, what you are developing. Uh, for example, not all the application requires a L3 to be 1 GB. You can actually reduce it, for example, or you if you want to increase, you can increase it. So looking from a different uh, peripheral or the MPU or the FPGA to SDRAM context, you get a different sizes and maps of the FP of the SDRAM. Now we'll be discussing in couple of slides the details about that. Who sees how much of memory, or who has the access of how much of memory? Yeah, that's something which I'll be discussing in the next slide. That what all the uh, what are the different peripherals or the different regions of the FPGA can access the HDRAM. Like I said, okay, like again, this diagram is this is the block diagram which a software engineer has to keep very handy, because this gives a very clear picture of what all things are accessible to him through which interfaces. For example, what are the bus weights? What are the peripherals connected to my switches? For example, like this is the L3 interconnect. This is the MPU subsystem. How is this L3 switch connected to MPU subsystem? So it's connected through 64-bit AXI bus, and uh, L3 main switch is connected to L3 slave switch to 32-bit AXI bus. Of course, this is all hardened. That means since it is part of the SOC, so this part is something which you cannot change. But through programming, you can actually access all these features. So L3 peripheral switch, as we discussed in the higher block diagram, all the high-speed peripherals are connected. On the L3 slave switch, we call L3 peripheral switch, we have all the slow peripherals connected. And important on the L3 slave peripheral switch, you have a lightweight HPS to FPGA bridge. So today in lab we'll be using this bridge, and through this bridge we'll be actually accessing this slave and connected to a DOT which is there in the FPGA. Now again, I want to bring you back to the physical memory mapping. So let's see how a FPGA can seize the SDRAM. So FPGA sees this SDRAM from this master interfaces, that is FPGA to SDRAM master interface, and it directly gets connected to your SDRAM controller subsystem. Now, with this, what happens is your FPGA can actually see entire SDRAM memory space from 0 GB to 4 GB, like the entire SDRAM space. So that's very simple. So entire SDRAM is viewable to, or is visible to FPGA. Okay, now how does the MPU sees, or the microprocessor unit sees SDRAM? So using it has this interface which sees or accesses this SDRAM controller, and it can see, actually it has access to, MPU has access to lower 3 GB of SDRAM, and kernel manages and can allocate memory in this 3 GB space. So, yeah, so you do any malloc, or say you want to reserve some memory, you can actually use this SDRAM region. And just thought here, so say suppose you want to actually share some memory to your accelerator or a DUT function which is in the FPGA, you can actually access this SDRAM region, or you can allocate some part of this SDRAM region and then make it accessible to FPGA also. Now this is MPU to FPGA part. So of course these are so this is the 960 MB of FPGA address space is visible to MPU, and MPU can access to MB of FPGA address space via this lightweight bridge, and and 960 MB is actually from this HPS to FPGA bridge. You can actually get more details of this through a tutorial which is there in developing Linux drivers for custom peripheral workshop. And actually, you can go to rocketboards.org. I'll That's there in the last slide, or I would say in the references slide, where you will get all the example designs where you can get started, or uh, the the references where you need to get started. So I'll also point out to where you can find that link. But remember, that's available in rocketboards.org. Now, moving next is FPGA to FPS, as we discussed. This was uh, discussed before also, that FPGA can see the memory, and it is 4 GB of memory space. And also, apart from this, as we discussed, right? So this From this master, you can actually access all the SDRAM region, while even from FPGA to SP bridge, which is a high bandwidth interface, you can actually access the SDRAM. So these are different options which a software engineer can use while developing uh, any application which includes FPGA and ARM code. Now, a little out of context, I would say, but very important for today's lab. And since we are in the memory map region, I thought I'll have this as we discussed, right? So that this is ARM core, and these are dual core ARM, and then we have DDR controller here. This is a simplified diagram, by the way, just trying to show how today's lab is going to look like. So, say we have this, you have a code running on MP microprocessor, while you want to access a peripheral which is sitting very far on the L3 switch, L3 peripheral slave switch. You can access actually via memory map bus. So this is an internal AXI bus, and then it all goes to the PIO. But the good thing is like you have all this buses internal connections, and then you have your own peripherals which you want to connect, which you want to develop in the FPGA. How do you actually make sense, right? How a software engineer writing a C code wants to know what all peripherals are connected here and how do I do the address mapping of them? So that's where I think that's the obvious question which you would have got by now. Because this looks very complicated from an architecture perspective. But how do you make it simple for me? Which is a very valid question. And the next part, actually, I think rest of the today's talk will be more on that part. How we simplify your journey on this kind of complex SOC architectures. And as discussed on the other day on the ARM architectures on we have ARM core on Cyclone, ARIA, and Statix 10, and now Agilex. So this subsystem complexity keeps on increasing. For instance, like you have Statix 10 and Agilex, we have 64-bit A53 quad-core CPU. Uh, and then peripherals are there, and then we have high-speed interfaces are there. So how do you make really things easy here, right? How do you really address them easily? That's what we are going to look now. And just remember this part of the diagram. We'll be taking a look of this in our lab also. Okay, so we have completed one part, which is SOC architecture. Now we are all set for understand. We are all set with the information of what is SOC, what all peripherals we get, how they are interconnected each other internally, what features those internal peripherals are there. So we will now that was uh, that was a one step to get into the coding part. Now let's see how actually you can start developing your code and what do we provide you to make this journey easier. Okay, so because can we take few questions? And I think I'm going a little too fast, but this was just a recap. And these all, by the way, all the architecture details can be found in the reference documentation and the user guide of our Cyclone 5 SOC. In the
Yeah,
reference slide,
uh,
we have included the links.
correct. Ritesh, I have also pasted the rocketboards.org link on the FPGA, I mean, on the chat window. So all participants can take a look at the rocketboards.org. Right? And there were
Sure.
some of the questions which are more towards the ARM community. So I would like the participants to know that, this is an ARM processor sitting inside the FPGA. So some of the queries you might find answers in the ARM developer community website as well. So some of them have been answered in that way. So, Ritesh, there was a question where it says, what is ACP and how it is used? So, how it is used, I could find the link in the ARM community and I've pasted that link. What is ACP, probably, if you want to take up that question?
Sure. Yeah. So ACP full form is Accelerator uh, Coherent Port. So so what does this ACP? Okay, I'll go to the slide so that I can explain better. We have a coherency slide, right? Right here. I'm sorry. I'm just going.
I think
Okay.
you were there. It went
Yeah.
ahead.
Right. Right. Yeah. So
Yeah.
right. So this is yeah. So ACP ID mapper and ACP together makes this possible for uh, coherency possible. Okay, so ACP stands for Acceleration Coherency Port. So basically, okay, I gave an analogy of coherency. Right? So basically, any there are okay. Let me step back again. See, we are talking about two subsystems on a single package. That is, you have an ARM subsystem and you have FPGA subsystem. Now, FPGA, you say you have your own IP. Now, you would call it as IP or say Puneet calls as DOT. Now, both are same for now. Okay. Now, say your IP and ARM both are working together. They're working together means they are doing some part of they are solving a complex algorithm, and both are working to solve that common problem. Now, for example, let's take you're doing a matrix multiplication, and say you want your main program is in your ARM and you want matrix multiplication to happen on the FPGA. So you build an IP to do matrix multiplication of floating point integers. I'm sorry, floating point data type. So, so floating point matrix multiplier is implemented on FPGA, while your CPU actually takes the data from say a image and extracts that data, converts into floating point and sends it to the FPGA. Now, uh, for some reason, FPGA wants to know where is my CPU, what is my status of the CPU, or wants to actually check some data which is there in the cache memory. He wants to look into the cache memory. So FPGA IP can actually sync with the cache memory controlled in the CPU through this ACP port and then decide what next it has to be done. I hope I explained the basic idea of why ACP is used.
Yeah, Ritesh. So the next question would be, out of the 4 GB memory, can MPU access only 3 GB memory? What about the rest 1 GB?
Yes, I think it's a
I think, and this
MPU.
question of the coherent, I think the person has said, looks like they got the answer.
Thank you. And yeah, so I think this is one. So that right. So the SDRAM region that is 3 GB say MPU is accessing. So other 1 GB of space is all given to the FPGA slaves and HPS slaves. So ideally, the MPU can only access the 3 GB. Yeah. So, Vikas, can we go to? I mean, can we move to the next section now?
Yeah, I think we can move. I don't see any more questions. If the questions are there, then we'll try to answer it on the chat window itself, on the Q&A window. Sorry.
Sure, no problem. Sure. All right. So yeah, let's move to next section, which is development flows. So uh, as you know, there are two different development flows because uh, we are aware that if this SOC uh, is a heterogeneous device. Heterogeneous means there's the ARM core and there's the FPGA. These two are independent computing devices. And traditionally, these two uh, computing device has their own language, has its own development cycle, has its own way of programming them. So ideally, these are two different worlds: hardware, that's FPGA, and software, that's a microprocessor. But then when we put it together as a SOC, definitely we will be requiring two different flows. But then we have a question: can we actually merge them, or can we actually try to see if both can be done in parallel, and then somewhere we come together, software development flow and hardware development flow come together and work together on a to implement something on these SOCs. To do this, this is the industry flow. Basically, it's a conventional flows on the both sides. But then I would like to show how we actually, from as an SOC uh, vendor, how do we actually to take these two to merge these two, or I would say how these two can go in parallel, and software engineer and hardware engineer can work independently. Here on the left hand side, as you see, we have Cortex Prime Pro, and okay, so this is we discussed in day two. Vikas demonstrated or took the lab on how to open Cortex Prime Pro, how to compile a design on Cortex Prime Pro, what is platform designer, how do you see IPs in the platform designer, standard RTL flow, that is your how do you write even Verilog code, uh, and IPs. I think IPs is something which today we'll have a look into it, because we'll also see how our we'll also create a small IP, by the way. So we'll have also a look on that. And then traditionally we have simulators. So Model Sim, which is from Mental Graphics, VCS from Synopsys, NCSIM again, Cadence. So we have multiple vendors and supporting our simulation flow. So also I would like to call out here that see we have our IPs actually can actually generate scripts, which these two can just take the script and run, so that you don't need to compile each and every file one by one. So it's all there in the script. You just have to say run a top level script which internally calls out multiple scripts or multiple files. That's part of the design flow. And then we have debuggers like signal tap debugger and system console. Today we'll be using system console to see how do you debug or how do you see the data or how do you see the data into FPGA. And Cortex Prime programmer. So today we'll be also using this programmer to program your FPGA. Yeah.
Ritesh, I would like to just pause here for a moment. For all the participants, we would like to reiterate here is what we are trying to do in today's session is, to show how you can use the ARM processor within the FPGA. As I see, most of the questions are more targeted towards the computer organization or the processor world and how the processor actually works. So actually, that is not the idea of covering this particular. The topic for today is actually, how to make use of the processor within the FPGA, and for that, we just gave a very brief introduction of that particular aspect. And while we are trying to answer most of the questions on the processor side, I would really encourage the participants to look up at the ARM community to understand how exactly an ARM processor and all the peripherals would really work, right? But our concentration for today is how to make use of processor sitting inside an FPGA, right? And how to talk between an FPGA fabric and the processor. Yeah, Ritesh, sorry for interruption. Just go ahead. Yeah. Ritesh, you can go ahead.
Sure, Vikas. Okay. Yeah. So on the right hand side, you'll see the software design flow. Now here, this is actually our today's topic, and more on this part, that the how do you design a software using our development tools like uh, SOCEDS. And SOCEDS, the part of SOCEDS covers all these orange color boxes which are there here. Like it contains ARM Development Studio. Again, this is released from ARM themselves. Then we have OS and BSP supports, OS like Linux, VxWorks, and hardware libraries, which will help mm, build your drivers on top of the or the peripherals actually. And then we have example designs which you can get started with. Simix model for simulation. So that is one of the one simulation tool available in the software design flow. But again, Simix is these models from Windrivers uh, and model and then the debugging capabilities. So debugging capabilities we'll discuss a little bit more on the next slides. So how you can actually debug your design from ARM Development Studio and also using GDP. And GDP is an again GNU project, open source, and of course the ARM subsystems are capable of this feature or of using GDP for debugging. And then to say you want to program this FPGA, so you can actually use the HPS Flash programmer. So this is the typical software and hardware development flow. And the here, if you see the handoff files, so this goes from the hardware to software, because in one of the slides we discussed on the PIO, the LED PIO connected to the subsystem. So suppose you have an IP, which is you have built an IP in your hardware design flow, and you want to memory map it to or memory map it, and your software has to access those peripherals. So how do you provide those informations to the software? So that's through the handoff file.
Ritesh, just explain what PIO is. There was a question, I've answered the question, but still it would be in the larger
Right.
interest.
Okay. So PIO is actually our is an IP from Intel. So PIO stands for peripheral IO. So basically, any IO connection you want to do it on the FPGA fabric, you can use this IP from Intel, which gives one side, it gives an okay, I can draw, sorry. Okay. So for example, say this is FPGA. Okay. So this is SOC.
Maybe you can just bring the photo of that board and quickly just show it on the board itself.
Yeah, here we are. Yeah. So here, so right. So this is your Avalon memory mapped interface, a Avalon memory map, and this is an FPGA. So PIO, peripheral IO, gives a connectivity to their IOs, which is the LED or a switch, to and gets it memory mapped to the bus. So basically, using your API call on the ARM side, you can actually control this IO interfaces without really worrying about the without the timing of the control, or worrying about the addressing of the IO. So PIO is our IP from Intel. Okay, now let's. Okay, so this is the high level high level flow of FPGA design and software design. So we spent some time in the last slide explaining. Traditionally, we have a FPGA design and we had a software design flow. Now, if FPGA engineer used to program FPGA and CPU software designers used to program the CPU or a software code into it, both used to talk through a, common interface, might be PCIe or any other proprietary interfaces. But then, uh, when this data transfer is happening between both of them, so both has to sync, and extensive documentation needs to be done. The both engineer or both the teams has to sit together and understand how a FPGA has to talk to CPU or how CPU has to talk to FPGA, and a lot of time is consumed there because uh, both the teams has to be in sync with each other. But with our flow, when we have an ARM core or CPU in it, so can actually FPGA engineer can focus on the FPGA part while software engineer can focus on CPU part, while the interconnect part can actually be left to the hand of files, where handoff and it takes care of all those integration, takes care of abstracting those handshaking at a higher level. Okay, and so our SoC EDS provides this automation of hardware software handoff. So provides this confusion of both the design worlds, the hardware design and the software design worlds. So typically, yeah. So SoC software provides or SoC EDS provides your ARM DS5 with compilers and as well as Eclipse-based IDE. So it provides an abstraction of CPU and FPGA development. You can actually profile, debug, and cross-trigger the debugging. Now, also it enables you with the SoC EDS. We also enable you with Linux. We'll be covering the OS. We in one of the slides we have what all OS supported and what is our ecosystem. Basically, third-party OSs. Hardware lips. Basically, hardware libraries are your peripheral accesses, which you want to access different peripherals with OS and without OS, and enabling FPGA benefits with acceleration, offload, IO expansion. So your question on PIO was actually on the IO expansion and software interface to access the FPGA. So that's again with the handoff files. And no proprietary or additional tools required. So again, even you can get started with ARM DS5 with a basic license, which is the all license for 30 days, or you can actually compile with GCC, which is Linaro GCC available in the tool in the SoC EDS. So let's see about what all the tool supports we have on the EDS part. Like which all FPGA support, what edition of the SoC EDS. Starting here, we have ARIA 10, Statics and Agilex SoCs supporting your that are supported to Intel SoC EDS. I'm sorry. Intel SoC EDS Pro Edition, while Cyclone 5, ARIA 5, and ARIA 10 SoCs are supported through Intel SoC EDS Standard Edition. Again, you would see ARIA 10 here and ARIA 10 here. We recommend ARIA 10 SoC development on Pro Edition. So today, as again, we have shared you the download materials and download links for a standard edition, because Cyclone 5 are supported on the standard edition. Today we'll be uh, taking a lab on Cyclone 5 SoCs. So this is again a quick look. Many of you have this question about what's included in different editions. What is this Pro and what is this Standard edition? So basically, ARM DS5 Community Edition, this comes with the standard. ARM DS5 Intel FPGA requires, it comes with the Pro edition. So there are a few questions other day about the licensing part. So again, this DS5 Community Edition is free. So so again, DS5 uh, comes with Eclipse IDE and debugging over Ethernet. So these are again as part of this community edition. On the hardware to software interface tools, the device tree generator, which is very basic, and that is part of this, part of the both the tools, and community edition, which is free, can actually it comes with it by default. Compiler, yeah. So Linaro Linux GCC toolchain, which is ARM Linux ARM-Linux GNU ABIHF hyphen GCC actually. So uh, this is again a GNU project. So it's a free info which is supported in the SOCEDA standard edition. And of course, since ARM compiler is actually uh, is a proprietary, it's only supported on the licensed version. So libraries again, because to start with Cyclone 5 and starter edition kits, so we provide extensive supports for Cyclone 5 on hardware lips. Most of the peripherals do have BSPs and driver supports for those peripherals. And example design, yeah. So this is important, which is uh, golden hardware reference design. In this hardware reference design, uh, we provide Linux binaries, SD card image, and the hardware example design. So all those things are part of the golden system reference design. So with this includes GHRD plus Linux binaries plus SD card. So all to get started, and today we'll be using that GSRD, because we don't want to take time in say compiling Linux binaries. So because Linux binaries are all commonly used, we'll see in the subsequent slides. But of course, for our information and for our uh, understanding of how this works, we'll be also talking what all tools supported if you want to create. So suppose you want to build a Linux kernel which is not supported today, or the next generation Linux. Can you contribute to this community? So do we provide those tools? Yes. The answer is yes. We provide those tools, and we'll be discussing those in the subsequent slides. Uh, yeah, so we talked about hardware libraries before. Hardware libraries are part of SOCEDS, and it actually they enable software engineers to take advantage of multiple peripherals, and software development gets accelerated, or quickly you can develop a software without worrying about the drivers and the low level hardware libraries. So these are many of our supported peripheral hardware libraries. Yeah. So this is a interesting question. So I do develop my uh, system or SOC subsystem with say ARM core PJ in kind of a complex design. How do I actually debug? And when we talk about two teams interacting together to develop to complete a project, how they can efficiently come together, and that they can actually debug together, because you don't want to always blame on someone saying no, this is not my software problem, it's a hardware problem. You don't want to have a situation where you don't want to see hardware engineer saying, no, no, that's not my problem. This is a software issue. So these kinds of things uh, may happen, and if you don't want to, if you want to avoid that, we need to have a robust debugging tools where we find a root cause analysis without superficially just say that no, this not might be problem in this section or that section. You really need to go to a detailed analysis. So uh, that's the debugging, because all the like most of the design requires debugging. But how do you debug all the areas? Like you need to debug drivers, you need to debug the code, and you need to actually optimize the design. You might not get performance at the first stage, but then as and when you keep optimizing, but then during optimizing, you need to have an insight of how things are working, or where is one clock cycle getting wasted if you want to see. So how is it possible? So these are all questions being answered with the SOC EDS actually. So SOC EDS brings in an entire package of your debugging. Maybe it is a software side debugging or the hardware side debugging. So FPGA adaptive debugger actually removes that barrier where you need to use the USB blaster connection, and you will give a capability to debug both ARM and FPGA code. So single connection, so you don't need multiple cables running around and you try to complicate things. So basically, it's a bird's eye. You see the problem on top from a top level, and then you try to see where the things have gone wrong, or where your system is failing, or where my system is taking a lot of clock cycles or latency is a problem. Yeah. So one of the features of SOC EDS through FPGA adaptive debugger is to see the SOC peripherals. Now, like for example, you have a lot of peripherals as we discussed. We have, say, UART controller is there, you have I2C, CAN controller. So all those peripherals, you can actually view what are those register values. Or for example, you have PIO. The PIO actually has a lot of register values. So what, for example, you are controlling an LED, and in software you wrote to just simply you just have wrote a code to simple turn on the LED, and for some reason it did not turn on when you are trying it on the hardware. So you want to see where exactly my problem went, or where the things went wrong. So you can actually program using peripheral register description. You can actually go and see what data is being set. For example, if 000 means the software data has not yet reached my register in the FPGA. So that means there's some problem with your driver, or there might be some problem with the bus or the bridge itself, like that. Now, let's see of one of the other debugging techniques, which is really interesting to me too, because when we say this is heterogeneous system, when you want to implement few things on when you partition few things on software and some things on hardware or the FPGA, you need to see or you need to debug both together. You cannot, yeah, well, at one level you can isolate problems. You can actually simulate in your simulator. You can actually see how things are working independently. But then when it comes together, when you integrate the code, how do you actually debug it together? So you can use cross debugging techniques in FPGA adaptive debugger to do this. Like for example, you can actually run a signal tap analyzer. Now, signal tap analyzer is our tool in the in the initial slide you saw in the hardware development flow. In Cordas, the signal tap analyzer is there, and in that you can actually have all this, or few of the signals tapped into the signal tab to look to see the waveform what actually is running on the FPG. So basically, like you see it in a simulator like Model Sim or BCS. So you see the transactions happening, the wires and signals going around ones and zeros. So you want to see similar kind of structures on the FPGA hardware while running. So you can use signal tap analyzer, and uh, while you can actually run signal tap analyzer and use ARM DS5 debugger to cross trigger uh, this signal tap analyzer. So a little bit you need to know what is signal tap analyzer. So let me try to explain that. So you think like a oscilloscope. Signal tap analyzer is an oscilloscope to peep in or to view internal signals or wires of the FPG. Now suppose you want to hear what's happening on my 16-bit data bus, for example. You can actually go to signal tap, and you can actually pick up those bus or the 16-bit data bus and put it onto signal tap viewer. And then, but then you cannot capture all the signals infinitely because there is a memory requirement. Because those signals, whatever transactions are happening, gets stored internally. So you can have only finite number of samples. So you need a trigger point. So basically, whenever whenever that data bus is trying to change the value, I want to see what's happening and what's the value in that on the bus. So that might be one of the trigger. Or you might be you want to trigger or you want to have a trigger based on a valid signal, which is on say AXI valid or Avalon memory mapped valid signal or a read write signals. So based on those trigger conditions, you want to actually capture those data. Now, those trigger conditions also can be written hard coded in the FPGA, or but that becomes a very complex work. So you can actually use ARM DS5 debugger, saying whenever my processor comes and loads my data on the data bus, capture the data which is there on the bus. This kind of features can be implemented using cross debugger. So yeah, so this is what we discussed, that is SPS to FPGA cross debug. So based on your uh, code, where suppose I think you are all aware of the step debugging in the softwares. So using the similar concept, you add a breakpoint, and when the breakpoint happens in the software, you also capture the signals on the FPGA. Now, on the vice versa, you can actually have FPGA to trigger the HPS. So basically, whenever a signal rises on or there is a rising edge on any signal, for example, you want to instruct the debugger on the software to stop the execution of the software code. So even that is possible. With this, you get more flexibility to how you control your software and hardware to debug your registers and peripherals. Now, another is correlating hardware and software events. So, of course, there is always in the high speed kind of situations. Say, suppose your design is running at 100 megahertz, and like every 10 nanosecond, things are changing. So, you really want to see when exactly my data got changed, when exactly my uh, uh, when I need to stop my debugging, or when I want to have a breakpoint. So, you can actually capture a timestamp when the breakpoint happened, so that you can go and back calculate when was my program halted, what exactly this program created to halt. So with this, actually, you can have more insight of what's happening into the FPG. Now that was all part of the debugging. Let's move to operating system ecosystem. So as I discussed in the previous slide, so that we will be looking into the OS supported by third party and Intel. So we have over more than 20 operating systems supported on 28 nanometer and 20 nanometer SoC FPGAs, like even Android, which is from Fujisoft, or say FreeRTOS, or like freertos.org, or we have VxWorks from WindRiver, Micrium, Musi OS2 from Micrium. So a lot of other OSs. So any requirements on your OS, you can just have a look into this slide and say, and also on the rocketboards.org. So and decide to get started with your development of the software set. Now, this is an important slide where, because because we are talking about the software development, we embrace a lot of software or open source. Uh, uh, I would say open source projects or the open source flow itself, because the software development is like you need to. It's all about collaboration. So the more the open source we have a community built up, and we get to solve our problems with the help of community, and with the help of uh, with the help of community, we can actually go much farther. And that's where we have rocketboards.org, where all the technologies related to SOCs, all the software code, the Linux, the example codes, they're all enabled on rocketboard.org. Uh, this is the starting point. You can actually go to this website. It's a wonderful website where everything is there to get started. Even for even like step by step, all the small details are explained there. And it's a community portal where you can actually ask questions, you can give feedback and all. Then we have Intel Open Source Technology Center. So you can actually visit www.0.01.org. So one of the famous project is DPDK. Of course, that's something on the Ethernet side, but just trying to give a idea. So our acceleration stack, one of the major part of acceleration stack is OPAE, and that is again developed or hosted on one.org. And a lot of things are happening in this, a lot of community portal, or you'll say community contribution is happening on this portal. And of course, uh, we do a lot of we do sponsor on a lot of open source projects, and we adopt very early in our projects. Like for example, Linux kernels and distributions of various flavors. And of course, as we said, we have kernel updated and upstream. So the same open source methodologies are used for upstreaming the kernel codes. Linux device drivers, and high-level libraries such as OpenGL and OpenCL also. And we are all part of this open system ecosystem where Intel PH is actually a contributor or active contributor in open source projects. Industry best practices of Linux and enablement. Yeah, again, this is something we discussed in previous slide, but want to uh, emphasize that there's uh, uh, we have been contributing to this, and also we also support this Linux enablement or the Linux distribution. So moving next, how do I get started? So the starting point for the SOC development is to download SOC EDS and embedded development flow. So when you actually, this is the link provided, and when you go to this landing page, you'll see this something like this, and where you can actually select which edition. So this pro or standard, select the version. So current is 20.1. This is the latest release. By default, it selects the latest release, but if you want to go back to the old releases, If I'm correct, we can go up to 12.1. And then we have releases for both Windows and Linux. And you can actually download from multiple, like a download manager or download direct downloads. I guess currently we have support for direct download. Yeah, and yeah. So and this is how it looks, and also you can see how much the download size is, so that you can plan based on your bandwidth requirements. Yeah, and okay. So next part is okay. I got this SPDS software. I understood what is the ARM architecture. How do I start? So we do have a comprehensive list of or portfolios of SOC kits. Now, why do we develop SOC kit? So that you can get started quickly without worrying of developing the hardware. So the hardware is developed by Intel, but remember this is a development platform, not for production. So where you can evaluate all the features of the FPGA and SOC and take it to the production with this on using this development kit. As part of the development kit, we provide also schematic, board files, and all the required components, the list of required components, and all. So this is a good starting point for any develop hardware and software development. And so you can actually go to this page. This PPT will be shared in the drive, so you can actually go to this uh, FPGA SoC product families, and you can actually choose from the variety of boards, starting from Max 10 to the different flavors to Static 10 and Agilex devices. Different boards are available. You can choose. You can place an order, and you can get ARM DSY license included with it. Now, for academic, there were quite a few questions before, like what are the boards recommended for academics, where to get started. So again, yeah. So this is a Max 10 FPGA. So again, not a SoC, but to get started with the FPGA, Vikas session was based on the FPGA. You want to have a quick uh, I would say you want to program and see how LED blinks, or you want to program a NAND gate or a AND gate, and you want to quickly see the implementation on FPGA. So you can get started with this D10 light board. And yeah, just to remind you, this is the same kit which the top 5 uh, winners will be getting this kit. Yeah, and this is our advanced kit, which is D10 Pro, and this is for high performance computing. I just wanted to give a overview. This is from again from partner Terasic, but for universities they have significant discounts, and you can purchase them online also. So there's a commercial price and academic price. You can visit Terasic website for this board. So, Vikas, I'm done with this session on the first part. We can, before we go to lab, we can take questions, and we can actually spend some time on if there are any questions there.
Ritesh, I don't see any questions pending, but if any of the participants feel that the questions have not been answered, kindly repost those questions so that we can take it up again. I think Ritesh, we'll just wait for a minute. Firoza ji, do we have to have a break? Do we have any break right now?
Yeah, we have break from 12 to 12:30.
12
So
to 12:30. Okay, fine. Okay, so Ritesh, what we'll do is we'll probably wait for a minute. If there are no questions, then I think we'll continue.
Sure.
So there is a question, I think so. What is the Intel PSG? And yeah, there are a couple of questions right now.
Okay.
Right.
Ritesh, the first question is what is Intel PSG?
Yeah. So Intel PSG stands for Programmable Solutions Group. It's a group focused on FPGA or responsible for the FPGA product portfolio. So Vikas, Israr, and I are part of PSG group. Yeah.
Yeah, just to add to that, Altera was an FPGA company which Intel, bought. So in earlier, whatever was Altera is now part of Intel and is called Intel PSG, Programmable Solutions Group, where we deal starting from FPGAs to the acceleration and emerging AI and all those things. So the AI and acceleration, which are the new emerging fields in FPGA, will be covered on day 10, the last day. Right? There's one more question: D1 SoC versus Cyclone 5. I would say a D1 SoC is actually the board, and Cyclone 5 is the device which is sitting on the board. Ritesh, if you don't mind, can you just project the D1 board?
Yes. No
Or
problem.
so if you can just point to the FPGA and the whole board is called D1 SoC. And the FPGA sitting in between, that's the Cyclone 5 SoC. Whatever Ritesh is pointing out right now is the Cyclone 5 SoC device sitting on the DE1 SoC board. Now, this DE1 SoC board is actually designed and developed by a partner called TerraASIC. I have pasted the link on the chat window. So the TerraASIC manufactures various boards, especially for academia, and you can look up at the TerraASIC website for all the boards available from them for academia, especially. I think, do we have any more questions? Yeah, we have a few more
Vikas, I'll take
questions.
a quick 2 minutes break.
Yeah, sure, sure. Take a break. Yeah. D10, I think there's one question on D10 is only FPGA board. Um, no, I think there are many D10 standard, D10 light. So kindly, give the full specification, or you can go to the TerraASIC website and you'll get all the details. Okay. There's one more question. I installed Quartus Pro 20.1 and Intel FPGA Lite Edition on Windows 7. Is it okay for the lab session? Again, it's I think SOC EDS you will be able to compile, but you'll not be able to run. I think that's because you will not have the board. Again, compilation also depends on the kind of configuration you have. So it will be slow or fast based on the compilation. Right? What all languages we should be familiar with to perform these labs? Ideally, this is a C-based lab, but in general, the way the industry works is, the embedded side people code in C, and on the FPGA side people code in Verilog or VHDL. So usually, what happens is the Verilog and VHDL blocks which are coded in RTL will be flashed onto the FPGA side, and they will be accessed by the processor as a like a peripheral or a slave, as we call it, right? So what will happen is all the blocks on the FPGA side will be a memory mapped slave for the processor. So it's going to access all those peripherals or IPs or memories, FIFOs, all the things sitting on the FPGA as a memory mapped slave through the HPS to FPGA bridge. I hope that answers the question. Right. Is a standalone ARM-based microcontroller and FPGA-based ARM system. No, it's not the same. Standalone ARM-based microprocessor or a controller does not have a reconfigurability option, which means you cannot make your own hardware on a standalone micro controller built out of ARM. When I say hardware, I mean to say the logic within the chip, right? You cannot make a logic within the chip. But an FPGA, you can do plenty of things like I/O, different standards, different probably different I/O standards, different protocols, Ethernet, and things like that. Right? There's a big difference. There's a totally different product portfolio, as you may call it. Right? There's a lot of advantages of using an FPGA when compared to a standalone microcontroller per se. Right. So what I would say in one line, if you want to put it, Mr. Rajesh Saha, that you can make a microcontroller out of an ARM and an FPGA, but you cannot make an FPGA out of a microcontroller. That's probably in one line if I want to put it. Uh, Sorry, I see. I mean, light edition. It looks like it's a follow-up question. Let me try the first question. Okay, so I think I already answered. Okay. Which softwares are we going to use today? I think it's already covered D10, SoC EDS and Quartus tool. Do we get remote access to boards? No, as of today, you don't get remote access, but we are building it. Probably you might have to contact your college or your cluster, and based on that, you'll once the course is inducted, then you might get access to the boards remotely. Okay. Do we need to buy Cyclone 5 to run the code? Well, it depends. If you want to use it for your own project purpose, you can always buy the board. But today, I think we'll be showing it on the lab, and probably you can just do the compilation. Okay. What can we do after getting the FPGA board? Well, you can think of building your own projects. We talked about various domains on which you can work on day two. Probably I'll just try to repeat that today for the benefit of everybody. You can think of, working on, let's say, video analytics, video and image processing, DFT. A lot of people are building radar systems. Just give me a moment. I'll pull up that slide and show you different use cases which you can build. Uh, Cyclone 5. Firozaji, if you can just give me access to, project my slides.
Because
Yeah, sure, sir. Please, 2 minutes, sir.
No problem. I think Ritesh is back, so probably he can.
yeah,
Ritesh, do you have the day two slides, Cyclone 5,
yes,
the
page
last
number.
section?
Or
Probably you can.
Or should I give the permission? Yeah, I can.
No need. I think Ritesh will project it. No need. He's back.
Okay, thank you.
Okay. Thank you, Firozaji. Slide number 38. Probably you can start with 38.
yes. So industrial IP CCTV surveillance, right?
Yeah, motor control and all those things.
Yeah. So I'll just screen. Yeah.
Right. So you can take all these probably you can work in different fields, like CCTV is one project you can do. Can you go to the next slide? I'll just quickly cover these things again. Yeah. HD camera for industrial application. You can kind of, let's say you can think of making a project where you have a conveyor running. Okay. You have a camera which is seeing the conveyor. It detects a faulty product. You can have a robotic arm which can come and pick up the product and throw it out, or put it in a different bin. So you can think of different projects like this, right? What is the next slide, Ritesh?
Yeah.
Yeah, wireless backhaul. If you're working on like DSP and things like that, you can easily integrate an ADC, do FFTs, down conversion, up conversion, and things like that. So the next one. I mean, I'm just giving you all the possibilities we have. Probably the next one. Yeah, night vision goggles. This is a very good military application, right? These are all just to broadly say, you're working on video domain. You're working on DSPs. You're working on different aspects of your day-to-day life. For example, a simple point of sale machine can be built over using an FPGA. I think today a lot of people are working on electric vehicles. That's a new buzzword in the market. So you can think of building a battery management system. You can think of, IoT on the chargers, public charging. They're like, I mean, applications are renewable, right? And all are targeted
And
towards embedded.
yeah, and
Ritesh,
in
I think
this,
you can take over.
yeah, and just to add one, in this COVID pandemic, there are, yeah, so in the healthcare domain, a lot of these FPGAs are being used, like ventilator designs and all. So, okay, we'll get started with the lab part. I'm sorry, I think. Okay, sure. So thanks, Vikas. So we'll now start with the lab, but again, lab will only gets our hands on after our break at 12:30. But now just give you a brief about what we'll be doing, what is the target board, and kind of how this lab is being structured. So with the okay, so D1 SoC, as Vikas mentioned, it comes with ARM 5. I'm sorry, Cyclone 5 with the ARM core. So we'll be using that. And here, as these are the peripherals, just wanted to uh, provide a sneak peek of what all this board provides. This is one of the good FPGA or Cyclone 5 SoC board. It gives a good amount of resources or the peripheral accesses. For example, on the HPS part, you on the SPS you have Ethernet, USB, and DDR3, and then you have UART, accelerometer, and LTC header. Now today we'll be using the UART to USB because we want to actually see we want to actually access the Linux command line for command line interface. So we'll be doing through UART to USB. And then HPS also has a few reset buttons and then user LED. So one user LED for HPS. All from the FPGA side, we have yeah, USB blaster and then of course it is connected through Max2. But this you don't need to worry about. It is part of the board. But we'll be using this interface to load the FPGA binary. So JTAG programming, if you see here, it's connected here and here. That means you can actually access both HPS and FPGA. But today we'll be only accessing FPGA to program the binaries. Then we have a PS2 connector. If you want to connect any mouse or keyboard, the old versions can be done here. Then we have a dedicated SD-RAM 64 MB here. Then video DAC, where you can connect a VGA connector for a monitor applications or a display application specifically. And the video decoder, so basically you have a video input, the analog channel video, and then the audio codec, which is audio input and output, can also be connected on this board. And these are all connected to FPGA through to a I2C bridge. So you can actually connect it here. And then yeah, we have IR, RX, and TX. But again, you can do a lot of DIY projects using this board. And ADC, where you can actually connect multiple analog channels to this ADC, and then you can get the data internal to the FPGA. And to get started, like we have LEDs and then 7-segment displays. I'm sorry, LEDs are 7-segment displays, and a switch and switch buttons are provided. Okay, and the small black thing here is a flash memory, basically to store the since FPGA is a non-volatile device, we can actually store FPGA binary here, and on power on, FPGA binary gets loaded to the FPGA. You don't need to really have a JTAG always, because on field you cannot have this JTAG setup really. It becomes really uncomfortable. So yeah, so moving next, like yeah, so I don't know how do I. Yeah, so Golden System Reference Design, GSRD, we call that is this is available on our rocketboards.org. Again, for we like Terrasic boards, even Intel manufactures development kits, which was shown in earlier slides. So for all the development kits, the GSRD is placed on rocketboards.org. While for Terrasic board, you can actually visit the Terrasic website. And so basically, GSRD, basically the system which is provided with the board comes with a golden hardware reference design. So now this golden hardware reference design is your Cortex project. Now, like Vikas mentioned in the last lab, like we gave you a zip file and then you unzipped it, so you actually saw a project in it with a QSys file where you can open the Quartus platform designer. So similar. So we have you have Quartus project already built for you. You have all the pinouts or pin information for the FPGA. So all those things are taken care in the hardware, golden hardware reference design. So with using this GHRD, it actually saves a lot of time for you to get started. You really don't need to worry about what are pin connections, how do I constrain those pin connections, because when you start, you would be really looking for how do I really get set hands-on without worrying too much about uh, the complex things. So that you once you get confidence and once you get understanding of how these things all work, you can slowly explore how do I change the peripherals or how I can change it from a custom board. And then we provide a reference U-boot based bootloader. So this is again, we'll be taking today's U-boot uh, from the golden reference design. And then we also provide Linux PSPs and a sample Linux application. So what does this mean? So that means that once you get a board in your lab, with the help of GHRD or GSRD, you can quickly start developing your algorithms without worrying of uh, all the system related issues or without worrying about the setup itself, the initial setups. So that will taken care. Typically, this on the right hand side, you would see typical setup, and setup is also similar to today's lab setup is also similar, but I'll just quickly explain about that. So I have my laptop, which I'm currently hosting this presentation. Also, I have connected a USB to the board, and okay, of course, you just replace this board with a D10, a D1 SoC. As I said, we have a UART terminal, UART port where I need to connect it to my laptop. So I'll be connected through UART, USB. That's a USB to UART. Then you have a Ethernet where you can actually connect it to cloud. Now, when you get a when this boards will be hosted on the cloud, you can actually see this connection. But for now, you don't have this. I just wanted to show this for representation so that tomorrow you can actually access this board remotely. Now, again, another USB I have connected USB data. That's for programming the bit file or the bit stream. So I'll be connecting the USB blaster here. And since the Max2 is there on the board, I don't need a USB blaster cable itself, but I just need a USB cable. Uh, okay, again, at this point of time, don't worry about the USB blaster cable because not none of our most of our uh, development kits has the internal USB blaster, so don't need to worry about it. You just need a USB cable. On the laptop, these are the few of the software which are required. Serial terminal, like you need a PuTTY, which or if you are using a Linux, your terminal itself is good enough to get started. but I assume most of you are on Windows. So PuTTY would be a idle serial terminal. But again, whatever your preferred terminal, you can always use it. Web browser, if you are using a cloud interface, but let's not worry about it. SSH client also we don't need to. This is again if you need if this board is hosted on a cloud. System console, yes. So we need a system console today, and we don't need an ARM DS5 AE, but we need a SoC EDS. So again, we will just do. We'll not use today GUI. We'll not use ARM DS5 GUI, but we'll use a command terminal command line. Now, yeah, so on the system, as we said, GSRD, Golden System Reference Design, contains GHRD. Now, GHRD is your Cortex program. So this is the part which we discussed, which goes on the FPGA side. While the software side, as we discussed this side, which is U-boot, Linux, PSP, and sample applications, they're all part of this software code. And that goes to the SD card. So today we'll be requiring a SD card, minimum of 4 GB, and a SD card to load all this stuff here. So, okay, yeah, so we'll go to next slide. Now, what does this GSRD for Linux developer flow looks like? So this is something, suppose, uh, as I spoke last in the previous slides, that as a developer, you want to contribute to the Linux and you want to actually try out Linux, different Linux flavors, uh, and you want to co-develop your software. So you can actually start with the GSRD. So from the Cortex, we get a handoff file and a SOPC info file. Using the device tree generator, you can actually generate the device tree and the preloader. So this and okay, and then using the bitbake, you can actually take the Yocto release from the Git tree, and you can build U-boot, kernels, and root file system. And from the your C code or your software code, you can actually use ARM DS5 or a Linux GCC, which is Linaro GCC, to compile your application drivers or your custom applications. And all this can be put, or all this information has to be put in the SD card and then you plug this SD card to the board and you start running the code in the FPGA. This is the SOC EDS tool versions. So this keeps on changing, and that's why I have given you the link for the SOC EDS user guide. So all our documentations are there in this link, but UG stands for user guide. Then yeah, so we support Mentor Graphics, Bare Metal GCC. That's a sorcery code bench. So then Linaro GCC for Linux compiler. But remember, this is called as a cross compiler because you compile ARM architecture on your x86 platform. So that's why this is what it's called cross compiler. It's okay here. It's 4.8.3, but today will be. I have given you instructions to upgrade it. It's there in the Google Drive Day 7 folder. Please have a look there. Installation guide is there. It's called SOCEDS installation. So there we have 5. I guess 5.1.9 or something, which we have upgraded. And of course, we have ARM Core compiler, ARM compiler 5 and ARM compiler 6 versions available as part of the SOCEDS tool. Now, BSP generator. So sorry. So BSP generator now, this is one tool which comes along with the SOCDS. So BSP generator is used for initial configuration of the bootloader. Basically, and it uses the handoff files. The reason is you want to build a U-boot, and you need to understand what all peripherals my FPGA supports, or not FPGA, sorry, the ARM supports. And so suppose you're building a bootloader for, say, a new device, so you can actually use BSP editor to get started. More documentation details are there in rocketboards.org, and this link is specifically for Cyclone 5 and ARIA 5 FPGA. You can have a look there. So this is a BSP editor generator flow. So okay, so the BSP editor available in SOCDS enables us to create and manage the bootloader for Cyclone 5 and for Area 10 or Area 5 SOCs, and of course Area 10 SOCs also. Now this is something like, okay, so you have a hardware design and you have a Cortex Prime. Through Cortex Prime, you generate the handoff files. I'll be also showing you where the handoff files gets generated and what all files, what all the handoff folder contains of. I'll be showing it in the lab. Using the BSP editor, you can actually get the U-boot. You can actually create a U-boot image or a bootloader image from this BSP editor. I'm sorry. Okay, so going next. So this is the device tree generator flow. So basically, we have device tree generator. Basically, it uses the SOPC file and it creates a device tree blob, which in turn we can use it with the Linux kernel. And SOCEDS comes with boot or you can say SD card boot utility. So basically, you don't. This provides a robust functionality of writing into the writing bootloader into the SD card, because you don't want to corrupt the SD card or while using the third party applications for flashing your SD card. So we provide it as part of this. So it's called alt dash hyphen boot hyphen disk hyphen util. And if you type help, you will get the details of it. Basically, like write preloader to disk, or write a bootloader to disk, or write bootloader and preloader to disk. This is the general flow. Yeah. So I think let's take a break before we go to the next section. So so far in this lab we have seen what is GSRD. With GSRD, how do you quickly get started with our FPGAs and the development? Second is, how do you actually create BSP using BSP editor, or how do you create a U-boot and a device tree blob? So now let us, in the next section, we'll see how what is the boot flow in the Cyclone 5, and how do you create your SD card for booting a Linux? What are different components required? And again, I'll be taking GHRD, so it will be pretty easy. You don't need to recompile it. And then we'll be moving to Cortex. We'll be touching upon the Cortex compiler, and we'll be creating our IPs. We'll be compiling the bit stream, or we'll be generating a bit stream, and we'll be loading into the FPGA. And on the HPS side, we'll be writing a small C code, and we'll be compiling it using a makefile, and we'll be loading it into the FPGA. And we'll see the result through a system console.
Yeah, sir, actually, there is a participant, Mr. Gaurav Verma. So he is not putting his question to all. So we are getting his question. So can we address the question to you, sir?
Sure.
Yeah. So the first question that Mr. Gaurav Verma has put forward, can we measure on board power from FPGA?
Okay. So
Firozaji, was the question like, can we measure the board power from FPGA?
Yes, sir. Yes, sir.
No, I don't think we have an option to measure the board power from the FPGA.
Okay. And so there is another question. How can we measure the power of the design running on FPGA and MPU using board?
yeah. So again, you measure the current, and based on the current consumption, you can actually measure the power.
Okay. Thank you, sir.
No, I mean, I think the question, I don't know if I really understood the question, but if Dr. Gaurav Verma is asking, whether we have an internal register to measure the currents, like, internally, whatever the current is, if the value is stored in a register and it can be read out, if the question is something like that, then I don't think we have anything like that. Or probably doctor can write the question. I mean, what I feel is we may not have really understood the question well. Sir, if you can, put the question on the Q&A window, it will be great.
Yeah, Ritesh sir, I shared the question in your WhatsApp. If you can just check, and I will request Mr. Gaurav Verma also to please give the question to all section, because if you drop a question to me, I am not the right person to revert back to you. Thank you.
So we'll take a break and we'll come back by 12:30.
Sure, sir,
While
sure.
yeah, we'll take the question once we come back.
Okay, sure. Thank you, Ritesh sir. Thank you, Vikas sir. So all the participants, please be connected with us by 12:30. We will start sharp at 12:30. Again, I am giving the announcement for today's MCQ. We are having MCQ from 2:45 to 3:15. Please go through the instruction carefully. All the details are already provided in the instruction. Thank you.
Hello all, welcome back. So we'll start our session, and Vikas has answered the question for the power measurement. So thanks, Vikas.
So should we start with the session?
Yes, we can start now.
Yeah. Okay. Thank you, sir.
Sure. So in the first session, we saw the architecture of the FPGA, the architecture of the SoC FPGAs, and the development tools, debuggers, and now we'll be looking into the the lab materials and how actually you can get started with the lab. Basically, uh, we want to make things simple, so we want to we want you to quickly get started on this board. So we'll take the example of D1 SoC, but most of our boards follow the same steps. So so the steps are generic one, but only the package and the pinouts will get changed. So, to start with, so we'll first start what is Cyclone 5 boot flow. Again, little bit of basics or understanding how things works. So when you power on the Linux, the first, or when you power on the SoC, so first the boot ROM gets loaded. So boot ROM gets loaded into 64 KB of on-chip memory in the FPGA, and then it gets loaded. Uh, it's the boot ROM gets loaded, and then the preloader. Then it goes to preloader where it checks the clock, then IO configuration and status registers, pin muxing, DDR, and then it loads the U-boot into the DDR. Then when it after loading the U-boot, then the U-boot starts configuring the FPGA and loads the Linux kernel. Then once the Linux kernel is loaded, then your application can start running, or a simple Linux command line interface is available for you to say login into the root or your login name, and then you can start your operations on top of it. or execution of any application can happen from there. Or you can load a GUI on top of it. Okay. So preparing the SD card. So again, okay, so let me take a step back and come back. So this is okay. So hopefully you have yeah. So this is the drive link, Google Drive, where sorry, you would have downloaded the lab materials from the uh, drive, and the lab material consists of a zip folder, which is shown here. A zip folder. You need to download it, unzip it. So in the lab materials, you'll find 3 folders and a instruction PDF. We'll open this. Okay. And then in the drive, you will also see install SOC EDS and install linaro.sh. So I think that is something prerequisite, which I assume you already done. So just quickly to see whether our SOC EDS is working or not. So you need to type SOC EDS in the command or in the start search. You will see something like a terminal here. Just type SOC EDS and you should see a terminal there. And click the SOC EDS command shell and you'll see a terminal. So we have to type ARM Linux -Linux GNUEABI hyphen HF GCC and okay, sorry, and double hyphen version. So if you check this, you should be seeing a GCC, which is ARM Linux GNUEABI. This is a cross compiler. It's an ARM cross compiler, which we'll be using. So this is basic. So this is the mandatory thing which we require for this lab. Yeah, and so right now we have 7.5 version. Okay, we'll keep it aside. We'll see. We'll use it later part at later stage. Okay, now this lab material. Yeah, I'll be going through all the steps, which you can actually you can see the same steps here, but I'll just walk you through what is the content of this PDF. So a quick introduction of this document and then what are system requirements. 60 requirements anyway, we have already covered before the start of the session. Then FPGA hardware design, which we'll be first covering. Then HPS software design, which will include the header file generation, writing a C code, how to compile a C code using makefile. Then how do I prepare a SD card using TerraSec image, then power on the board, and then program the FPGA via JTAG, then accessing command line interface via UART terminal. How do I transfer the executor files to FPGA board? And then I will run the HPS part.
Ritesh, there is a request to increase the font size, like zoom in on the PDF.
Sure. Yeah. Yeah. I hope. Yeah. So by the way, in the drive, you can actually download this and you can keep it open for your reference. I'll be running through the same steps. And then the last part is accessing FPGA registers via system console. Yeah. Another thing. Sorry. Yeah, here we go. Okay, so okay, we'll keep it here. So yeah, so first part, like preparing a SD card, right? So you have to download a SD card image from the TerraSync website. So pre-built binaries. Uh, that contains the preloader, U-boot, device tree block, Linux kernel, and Linux root file system. So when you download this SD card, everything is there. You don't need to really compile the Linux kernels and BSP also. So everything is made available for you for this board, which is D1 SoC. Okay. Okay. So this part will take it, not an issue. I'm sorry.
Also, Ritesh, there's a question says SOC EDS command shell is not opening.
Okay, that might be an issue with the file itself. There might be a chance that SOC EDS is not installed properly, uh, or there might be issue with the memory requirement of the system. Okay, so sorry. Okay, so okay, so first step. So as I discussed, so here Linux. Okay, so from the TerraSync website, you need to download two things. That is SOC CD-ROM. So from here, we click here, and the Linux console. So Linux kernel current today will be using 3.1.2. You can actually have Ubuntu desktop also, which is available. You just have to download here. And from the CD-ROM, you can download. For me, my board revision is RevG, so I'll be downloading this CD. So once I download, so I can show that. So once I download, this is TerraSync folder which I created. So I'll be getting these two files in my system. So I will be doing. Okay, I'll be requiring this two. I'll unzip it. So once I unzip these two files, I'll be getting .image file. Now to yeah, so to load the .image file, you just have to use. Okay, I'll show. We'll use a SDRAM. Or
Ritesh, are you
I'm sorry.
sharing something?
Yes, but
Okay,
okay.
there's nothing on the screen as of now.
Oops. I'm sorry. Okay, I think now.
And here
Now you're
also, I
good.
think the font size has to be increased.
Yeah, this is the maximum which it
That's the
allows.
max. No, I
Yeah,
mean, this is okay. Like in the terminal, when you open the terminal, right there.
sure, sure. We'll do that. Yeah, yeah. I will do it right away. Yes, 28 should be good. Yeah. All right. So I'm going to insert my SD card into my SD card reader and into my machine. That's my laptop. Here we have this one. Now we we require Win32 disk imager. That's a program, and it selects by default the SD card. And we need to take up this. Okay, sorry. Okay, we need to give this path here. Yeah. So D1 SOCSD image, and then I will be writing to it. So it will erase all the data which is there in the SD card. So with this, we are preparing the SD card with the following images like preloader, U-boot, device tree blob, Linux kernel, and Linux root file system. Okay. So until this happens, I just wanted to show what will be our architecture of our design basically. Because before starting any design, we need to really understand like what is the architecture and what we are trying to do. So suppose this is an FPGA, and I'll partition it just to two parts. I'll I'll say right is the HPS ARM side, and this is the FPGA, and this size. Okay. I hope this is visible. Gus, can you give me feedback? Okay. So FPGA, HPS, and then okay. So what will be running is this DUT. Now this DUT is actually like okay, like DUT, or I will call it as an IP. And this IP is a register file, a register bank. So basically, it has reg 0, reg 1, reg 2, and reg 3. So these are four registers in this design. Yeah, and I'll be using okay, and this side, this is my lightweight HPS2 FPGA, or I would short formly call it as H2F bridge. I'll be using lightweight H2F bridge to write some values to my register this way. And here, anyway, I'll not go in details, but on a high level, this is my ARM core, or I would say A9 core. And of course, it is connected through a L3 peripheral L3 slave peripheral switch. So it goes this way, and then it goes this way. So ARM accesses the L3 peripheral switch from here. This bridge sends a transaction to the IP, and now in IP I have a okay. I would show this side Avalon. I need some space here, so I'll just put here AVMM. That is Avalon Memory Map uh, slave. So there is a bridge. So this is AXI. This is AXI. I would say 32-bit AXI get connected to AVMM slave, and of course this is 32-bit. So the thing is, this actually connection requires a bridge and or a bus converter. So this is again taken care in the platform designer. So this is what I want to show. That will be explained in the Quartus, and I'll explain how this IP can be developed and can be integrated into the Quartus flow. So this part we'll be doing using Quartus, and here on the left hand side, and on the right hand side, the ARM code will be writing a C code to write some register values here, and that will be as simple as writing doing a API call. Okay. Okay, so we have got write successful, and now what I'll do is, yeah, if I see here my folder, I have a SD card and I have a Z image and the DTB device tree blob here. So these two files are copied, and I will just make a folder, which, okay, I'll do it later part, not required right now. I'll just keep the SD card right now in my PC only. Let it be here. I'll just close. So this is one. So I showed you how to write the SD card or the preloaded images into the SD card. And the next is CD zip is there, right? That's a system which is I called it as CD-ROM. And from the Terasic website, we get the data sheets of all the peripherals. So basically ADC and audio codec, clock, all the data sheets which are there in the peripherals, we get all those. So that means if you need to know the details about what is that, for example, in FPGA, we have a data sheet for Cyclone 5. It's a good starting point where you get data sheet is like what all timing parameters are there, what is the voltage parameter and all those things of the FPGA. While handbook actually gives you more details about the device features and how do you use the device and all. So yeah, so like what is the LUT structure, memory structure, DSP structures, all those details that's there in the handbook. And yeah, okay. So this part we completed. Okay, and okay, and this is data sheet. Then we have a demonstration. In demos, they have basic of FPGA design. So basically FPGA to access ADC audio. Then it's a golden top. Golden top is nothing but like a GHRD, but it just doesn't have much project details, but just a top file, a SDC file, a Quartus setting file, and a Quartus project file. Yeah, so this is, you can actually start with these 4 files itself. So and then okay, SOC part contains all the SOC related, like in my my first HPS we have a C code, which is just a hello world program. So like that, you start with hello world and then access the GPIO, G sensors, and I2C switch, and like that. And SOC FPGA is like having both FPGA plus SOC together. Some say starting code like accessing HPS, accessing its LED and hex, or you can say 7 segment display from ARM side. So this project you can get started. If you go here, they will give they have hardware and software designs both. Hardware contents of Cortex design, software contents of all the code required, C code and all those things. So this is like a exploratory thing, which once you get the board in your lab, and then you download this and you can explore all the features of this board. Everything is ready to get started. So today, from the SoC FPGA, I will pick up this DE1 SoC GHRD. As I said, GHRD contains of a sample project, which is the QPF, Cortex project file, a QSF file, and a top file, GHRD top. So all those things along with the platform designer file called QSys. So all these files are readily available. That makes us gives us a one level of platform. On top of it, we can build our own designs. So I'm going to copy this file into my lab folder, and which I have did already. So you can copy from there, and you have to open this project QPF. I'll start my Cortex project. So Cortex Prime. I'll copy this link on this path. This is my Cortex Prime Lite file open project, and I'll paste my path where my this D1 SoC GHRD is there. By the way, I'm repeating. I have copied this uh, folder from the uh, Terasic untar folder, so that my reference example design is intact. I don't touch that, and I copy it and make a new. I start fix from there where I can modify or I can change anything. If something goes bad, I can always go back to the original starting point. So here we are opening the project. So QPF is a Cortex project file. So we need to open the Cortex project file. So if you see, Terasic has done everything for us. That they have also given us C5 or Cyclone 5, the device number which is there on the board, and the top file. Now, if I click top file, yes, so this is by Terasic, and this is basically all the I/O peripherals, all the I/O connections are mapped onto this top file. So you see input output declarations are there for all the peripherals like ADC, audio codec, all the clock inputs. So basically this has 4 clock inputs. And yeah, there are a few questions last time. How do I go and see what is my clock pin and all? So I'll just show that quickly. So go back to my Terasic folder where I downloaded the CD-ROM, and in user manual, I'll go and I'll open SoC D1 SoC user manual. So I'll go here, and you'll see clock circuitry. Everything is there here: board status element, board reset elements, clock circuitry, and peripherals. So in clock circuitry, this is the connection. So you have a 25 megahertz crystal, and then you have and then you have a clock generator, and then these are different clocks generated. For HPS, you need a 25 megahertz, so it's going to HPS. So by the way, this is FPGA, and these are the 4 pins on which I need to connect: clock 0P, clock 2P, 6P, and down they give where these pin numbers are there on the FPGA. Basically, pin AF14 is connected to clock 50, clock underscore 50. So on the top, in the top file, you will also see the same names, clock underscore 50, clock 4 underscore 50. It's the same, clock 4 underscore 50, clock 3 underscore 50, like that. So all the clocks are there. DDR3 memory, which are connected to FPGA part is there. Then we have hex 7 segment displays, and this is the HPS enablement. Basically, all the HPS IOs which needs to be multiplexed are here. And of course, the IR, RxTX keys are the push buttons, LEDs. Then you have PS, that's PS connector, switch, all VGA. So all those pinouts are given here. And next is we have a instantiation of the Qs of a platform designer SoC system. So this is the platform design project, which is called SoC system. I'll show it here back. I'll go back to my folder, the lab folder, GHRD, and you'll see here we have SoC systems. Okay, let me make it as large. Little small I'll make. Yeah. So SoC systems dot QSys. So this file contains all our platform designer project. So I have this entire instantiation here because if you see the name is same and then instantiation name in U0, you can give any name for it. And these are all the exported signals. Okay, so let's get started with that. So I'll be opening Pro Tools Platform Designer. It's open in my other window. So here it opened here, and I will open file. I'll open the QSys file, which is already there. I'll do file open, and in the GHRD folder I have SOC systems.qsys. I'm going to open that. It'll take some time, and it will open, and we'll see the basic platform designer design which they provided. And okay, so for this lab to upload into the drive, I have created the register bank also, but I'll just delete it so that we'll do it again. Okay, so this is the example design. I would say this is the HPS systems platform design provided by Terrasic, so or GHRD. So we'll be using straight away that because there are so many settings which we need to do, and I would say instead of reinventing the wheel, we take the basic stuffs and we start working on top of it. So in system contents, you will see all this IPs which they are already instantiated. So HPS is our Cyclone Phi Aria Phi hard processor system. Now, if I double click here, I actually can see the parameters. So these parameters are already set, like how many bridges I want. So these are okay. On top we have general settings. What all if we need debugging features, we need to enable them. You need a cross trigger, you can enable them here. So all those things which we discussed in the slides are all there here. Then AXI bridge, this is important for us. FPGA to HPS interface. You can select up to 32-bit, 64-bit, 128. If you don't want, you can make it as unused. We'll keep their default 64-bit. HPS to FPGA interface, again, we can choose any of them. We'll keep it as 128-bit. And lightweight, since it's lightweight, it's just 32-bit because you just have to control few registers. So this is not for high bandwidth transactions. It's for small data transactions, or few bytes of the data can be passed from the FPS to FPGA. You can actually, if you don't use it, you can make it as unused. So we'll keep it as 32-bit. And then as Vikas showed that we can have peripheral pins, different peripherals can be used. And then as there are few loaners which can be enabled here, few GPIOs can be enabled here. So those key things will keep as it is by default. Let's not go into that. This clock, if you see that oscillator, directional oscillator 25 megahertz, that's why you would see in the user design. I'm sorry, in the user manual, you will see this 25 megahertz coming in. This is the HPS clock 1 and 2. And this is because we have enabled his 25 megahertz. It's not recommended to change here because if you change, the hardware needs to be changed, or the vice versa. If you change in hardware, you can change it here. SDRAM, yeah. So this is the common SDRAM which we discussed in the first half. So the DDR controller, all the parameters related to this can have memory parameters, board settings, and all. So basically, these are all. This is more on for the board related settings. Software settings are done all through the drivers and the application level code. Okay, now moving to the system or system contents on the platform designer itself. So what we have is we have a HPS, hard processing system, on-chip memory. So you just double click, it goes to parameter editor. You see there is a 64 KB of on-chip memory, and you how do you see who is accessing this? You just have to click on S1. So your HPS to FPGA AXI bridge, which is 64-bit wide, is actually connected to the it's connected to the on-chip memory like that, and then there is a JTAG to Avalon master bridge, which is connected to the on-chip memory like that. Okay, let me come back to this diagram. I just want to specify what is JTAG to Avalon master. I'm sorry, I'm just trying to switch between the slides, but screens, but please bear with me. So JTAG to Avalon master bridge is something which we are going to use today. So I just show you what that mean is. Okay, like for example, I say I have this. This is an IP. So JTAG, yeah, JTAG to AVMM bridge is a IP from Intel. So it actually gets connected to. So on one side here, yeah, on one side it's a Avalon. So on the top it is Avalon memory map, and on bottom it's a JTAG. So I would say it's something like this. I connect it to JTAG. These are the JTAG signals. It all goes. This is a USB cable actually, and it goes to my PC. Now this is my say laptop where my Cortex is running. My laptop where my Cortex is running. So this is the USB port. Through USB port, I have connected to JTAG on the board, which gets connected to the JTAG pins of the FPGA. And this is JTAG. On the other side of the IP, I have Avalon. And Avalon master goes and connects to my slave of my IP. And this is exactly the same thing. This is JTAG to Avalon master bridge. On the master, this is Avalon memory map master. I have connected multiple IPs. One of them is on-chip memory. So similarly, I'll be connecting to my register bank. Okay. Now, in this diagram, I have just showed for simplicity my IP, but there are many IPs already connected in this FPGA. But for clarity, we are just keeping it simple.
Ritesh, just a second.
Yeah.
A small announcement. I think the whatever steps Ritesh is following is already mentioned in the day7 underscore lab underscore HPS dot PDF available on day7 underscore lab underscore SOC. It's a zip file which has already been uploaded on the Google Drive, which has been shared with the participants.
Yeah. Thanks, Vikas.
Okay.
So I'll just go one step back. So if you don't, yeah. So as Vikas said, day7 underscore lab underscore SOC dot zip. This is you need to download from the Google Drive. Once you unzip, you'll get this folder, day7 lab SOC. In that, the PDF is there. Yes. So, okay. Now this is GHRD. Now I want to add my own DUT or my own component. How do I do it? So basically, I need to write my code first. So I'll be starting with that. But to save some time, I have written my own. I have written this code before. IP. So I have kept this in the IP folder, in the GHRD folder, in in that subfolder IP. Yeah, this is better. I'll just reduce this. Yeah, I go to IP, and these are all four folders provided by GHRD, so I'm not going to touch them. I have created my own folder called my IP. In my IP, I have a register.vht. So again, this is the solution. You can actually see this. This is part uploaded in the drive as well. But you can actually start writing your code. I'll just open this. Yeah. So this is a VHDL code. Again, I wanted to bring in some variety or kind of a diversity in the coding styles because yeah, uh, Vikas showed a Verilog with system Verilog construct. Puneet is taking up Verilog. So I thought I'll also touch upon VHDL so that it's fair to show all the most of the industry um, languages here. And of course, our support to all those languages, seamless support to all those languages, right? Yeah. So yeah, so all our compilers and even model sim version of the for Intel FPGAs, they also support the mixed language compilation. Okay, so I have an entity called register. Yeah, I'll just increase my. So I have a register. I'll have a clock in and a reset port, and this is the Avalon memory map slave interface where. Okay, so again, so you might be aware by now about the Avalon memory map. Of course, Puneet has discussed it one of the course in one of the class, and so but another for just for your information, Avalon memory map spec is available. It's you can get it freely available on the Intel website. So you can see here Avalon interface specification, and in Avalon memory mapped interfaces here. So this is the and these are the signals required basically. Write clock and write data like that, for example. So these are the signals required for the you can refer this document for more details. So the same these signals are taken from the same document, like what are the mandatory requirements of the interface. So write is required, write data is required, address is required, read data valid, and wait request. Now, just make sure that this is the good practice of naming conventions. I'll tell you why. It's good to have AVS first name because it's a slave, Avalon slave, and from who is the master? HPS is master and FPGA is slave. So always name it as master underscore slave. So the names can be anything, but it's good practice. And these names, try to keep it as same as possible on the right hand side here. Right data, address. Of course, you can change them, no harm in it. But our tools, it automatically recognize these signals and it maps it easily. Otherwise, there will be a lot of errors. You need to fix them. So becomes a little cumbersome. But I would recommend to have this set of names kept as it is. And these are standard specifications, so no need to change them. But on the left hand side, you can always change them based on your module. Yeah. I could have written actually register here, yeah, HPS underscore register, because this name is registers. Yeah, but FPGA I'm putting. Yeah, and then I have declared in the architecture of the VHDL code, I have declared 4 registers. This is 32-bit wide and few signals. And okay. So now in this process, in this process, I am handling both read interface and write interface. So this is the write interface because I am looking into write data, write signal, because this is actually, if you see, it's an input. Input, looking whether the input is high, and then I will latch it. I will do address decoding. You see your address. I'll decode the address. If it is 0 address, I'll put in red 0. I'll put write data into red 0. I will repeat again. So in this process, I am managing or handling write interface, and I'm doing using write signal. I'm looking at for a write if it is going high. Then I'm decoding the address based on the address values. Either it is 0, 1, 2, 3. I'm loading the write data into my register. Now, for others, I'm doing nothing as of now. You can have our logic change later. Then for read interface, again similar to write, I'm watching out for read data on the read signal. I'm looking if read is high. If it is high, then or I would say, I put it in right words. If read is asserted, I decode the address. If address is 0, I'm just going to load the address, or I'm going to load the read data bus with a reg 0 value. And then I'm going to assert a read data value, which is 1 for a clock cycle. Or ideally, I should load it until the master has accepted it. So I'll be loading based on the address, and will be loading the proper register values here. So this way, any master who is conforming to my Avalon interface specification can write into reg 0, reg 1, reg 2 based on specific addressing, and can read from these ports uh, from the reg 0, reg 1, reg 2, reg 3 registers. So uh, that's my design. And wait request, as of now, I'm not asserting any wait request. It's always 0. Basically, wait request is for back pressure. So suppose, okay, this is slave, right? So just think, okay, master has asked, okay, I'll go to my design, my architecture. Say, okay, so this is master actually, right? And this is slave, as I mentioned, this is slave here. So master is going to access this register. So if this IP is doing something else, I mean, it's computing. For example, you're doing a matrix multiplication, and this master immediately asks for results. But this IP has to do some computation, and it needs to tell this master to wait for some time. So this IP is going to assert a wait request to the master saying, "Master, I am busy. Please wait." And until wait request is high, this master is going to wait and probably not send a next request. Of course, it can queue the request, but there are a few implementations which we say, okay, it is again architecture specifications. Still, you can say, no, I'm not going to send my next request until the first request is served. Because one of the reason is because this doesn't have an transaction ID. So you just need to wait until this completes. So okay, so we were in the code, and I think, yeah, that's but right now this IP is simple. It doesn't need to wait for any computation. It's just like, it's like an accumulate. It's just a register. Write some value, read some value from the same register, like a scratchpad register. So I don't need to wait for some computation. So I'm just keeping this wait request 0. And another thing, just for, yes, so this is important. So in the spec, you need to look out for the timing specification. So this is how, based on this timing, I have written my code. So just think, a write request is raised and a wait request is there from the slave. Once the wait request is low, the master is going to accept my write data. And this is where, and after one clock cycle, my write is going low. That means the slave has accepted my data. And while read also, whenever master asserts a read, and say if wait request is high, is going to wait, and only when the wait request is down, the read data will be high. Or read data will be valid. You need to capture this read data from here. Yeah. So this is the timing. So basically, this code conforms to this timing. I would say this is with wait request. There is also a timing diagram with uh, read valid. So I'll
Ritesh,
yeah.
there are a few questions on, like which part is FPGA, which part is HPS. If
Okay.
probably you can just clarify on that, I think it'll be easy. Like, what is a generated code? Okay. And what will be the code which is done on the FPGA side?
Yes.
If you
So
can just
again,
show that and clarify, it will be good.
right. So again, from the architecture point, uh, this IP registers.vhd is my, okay, yeah, registers.vhd is my VHDL file, and it is an IP which is in FPGA. And a C code, I will just name it as main.c, which I'll be showing is in the which is running on the HPS part. And again, to clarify, yes, I'll show here. So let me go. Okay, if you see this part, D1 SOC GHRD has to do something on the FPGA. This folder is completely for the FPGA part, while HPS underscore code is actually on the, this folder is entirely responsible for the HPS coding, and system console script is responsible for running it on the Cortex, which is running on my laptop for debugging or to see whether my results are proper or not. This runs on the laptop. Because I hope I have answered this well, but if you want to
Yeah, I
add
think if
up to
there are
this,
further questions, anyway, I will get it. So I'll flag it as and when it comes. Or you can
sure, sure.
continue. I think as of now, it's okay.
Yeah, sure. All right. So yeah, so I will also copy this in to make sure that we don't lose anything. I'll also copy this on the Google Drive. architecture diagram. Okay, now we were in the IP. So we were in the D1 SOC GHRD. We are now focusing on the Cortex part to add a DOT or your own IP. And I'm in the IP folder, my IP registers.vhd. So I just covered what is the code about, what this code does, and basically this code reads and writes from the Avalon memory mapped interface. This is an Avalon slave interface. Gets write request to write anything on these registers, and whenever a read request is done, whenever there is a read request, it loads the read data back or gives back this registration to the master. So okay, so again, okay, so not to confuse, let me correlate with where we are in this document, right? In the lab material, so that we are on the flow, on the track. So we are just in the hardware design. So we downloaded the CD. Yeah, so we opened the Quartus project. Okay, there's just one more thing here. Since this GHRD was developed in the older version, when you open it in a newer version of 20.1, it will ask to launch an IP upgrade tool. So just do that. It's just a simple step. Once you click here, launch IP upgrade tool, you open this, perform automatic upgrade. It will take some time, and it will give you will get a tick on the regeneration status, a green tick here. If there is some failure happen, you'll see a red mark here. But when you see green here, you just close it. All right. So that's then next is we are seeing the platform designer. Now in platform designer, first we wrote a RTL code in VHDL. Now we are going to create a component. So I just created a register component. So how do you create? Again, it was pre-created because I developed this lab before, so it's already there. But for not, you may not see this readily. Now, if you copy the GHRD folder directly from TerraSig CD, you'll not find this component. But if you download from the Google Drive, you will find it because it's already created by me. So how do you create a new IP file, new component, and it opens a component editor. You just have to give the name of the component, new like a display name. So what you want to display it here, and then description, and then you need to add the file. So basically, you add the register in the IP, my IP. You'll add the register.vhd, and you need to do synthesis to analyze synthesis file. So once analyze synthesis file is completed, it should be green. That means no errors. That's good. And then you need to go to parameters if you have some generic parameters or parameters in the HDL or Verilog file. As of now, we don't have anything, but most of the time you would have a bus width as a parameter, or you would have some integer value as a parameter. That time you can actually find this useful because you can actually drop just like you saw in HPS, right? We had an option to drop in whether the XI bridge is like 32-bit, 64-bit, 128-bit. Similarly, you can configure for your IP, but that's an optional. Yeah, so this is one interesting part while creating a component. So signals and interfaces. So here, if you see, I have given clock CLK.
Ritesh, you might want to expand this window. It is looking very small.
Okay, but for fonts won't be big.
Yeah, no, but I think it should be.
I don't think so. We have no, we cannot. Yeah, I would recommend to actually I have given link for tutorial. I know this will not be covering more details of this, but in this I have given a link for the online class how to create a custom component. So I would encourage to participants to go to this online tutorial or online training and get more details. Uh, but yeah, but just to inform, keep informed that since the namings, right, are important as I discussed in the coding. So since I have a clock underscore in, my clock port is automatically generated. I have a reset, that's why reset port is automatically generated. And since I have AVS in my name of the signals, my Avalon memory map slave is interface generated. If you don't give this name, this interface would have interpreted something else. Like, for example, we have so many interfaces, it would have interfaced randomly something. But since we have given good namings, it's already there. Only there are a couple of errors which I'm getting. So basically, it's saying interface has associated. It must have an associated reset. It's here. Associated reset. Just have to give reset here. And read valid must have support at least one pending read. Yeah, this is one where you need to go here on while you click on HPS FPGA Avalon memory map slave on the pipeline transfer, you'll have maximum pending read transaction. It is 0 by default. You need to make it to 1. Errors are gone. That's all. So, and then for exploring more about this, you can actually see the timing waveform. So this is what your timing, this IP behaves. So your master should actually uh, conform to this specification. So uh, like as is discussed. So same thing is there in our Intel Avalon specification. You can actually see the same here. Okay, so again, I'll not go in details of this. You can go to trainings, online training. I have given the link. I'll not save this because already I have a register bank IP created. Just another thing, when you create an IP, when you save it in your project directory, you will see a underscore hardware.tcl file. So it is a system generated. It's register underscore hardware.tcl file. So it's the same display name, register bank. So basically the same GUI, whatever you did, the same things are scripted into TCL. So you can actually go back and you can change the name here. You can actually, you can change the specification of your Avalon slave. You can change it, the read latency, read wait time. So all those things you can actually do it from here itself. But this is again optional. Once you create it from GUI, you don't need to touch this file. It's just for your information. So now in the project, we have a register bank. You have to double click. You will see here if since we did not code any parameters, right? I don't see any parameters. But then I just do finish. Now I see clock reset coming. So as we discussed in the day 2 class, we need to connect the clock here. It's just a clock connection from the clock source and reset connection from the reset source. So you see that the major two errors are gone because clock and resets are must. You cannot have any block without clock and reset. So this is a compulsory check. Now next thing is, as I discussed in the architecture, I need to connect this bridge to the AVMM, and I need to connect this JTAG bridge to my AVMM slave. So these two connections I need to do. I will be doing it through, I have here a H2F underscore lightweight underscore AXI underscore master. So this master I'll be selecting by clicking here. And I see a gray line which shows me a potential connection. I'll just mute for some times because there'll be slight noise from outside. fighter jet is far away now. Yeah. So, right. So this, when I select the master bridge here or a master interface here, I see a black line going down and then a gray. That gray line is a potential connection which I can make. It shows me an option, so I can actually go and just click on this dot, and it just connects. This is the good feature of platform designer, that you don't need to do a port mapping each and every signal you need to, don't need to connect it. It just, this signal gets connected means all your read data, read valid data, write data, wait request, all the signals are part of this black line. It's just that simple. And then I also need to connect JTAG to Avalon Master Bridge. So JTAG to Avalon Master Bridge. Again, I'll go and this is small dot here. I just connect. Now I got an error. So this is good. That error says that it's overlapping the on-chip memory. Again, when if you read the error, you are getting an error on master non-sec. So that's non master underscore non underscore sec. From here, I see this master is connected to my reg 0 as well as my on-chip memory. That's where this error is coming. I'll go here. I'll see this. This is something happening here. I'll just click here so that it does the sorting in ascending or in descending order. I can do it ulta. So okay, like this. So now, for example, it says there is a issue with this too, right? So always I can go and I can actually say reg. Okay, I'll do this. I'll go and I'll say 4 here because I have already 1, 2, and 3. Uh, this is start address and this is end address. I'm sorry for the bad. I mean, font is very small. I think I cannot. I'm not sure if I can increase this font. Yeah, but yeah. So basically, there is a start address and end address. I just need to change the start address because it is overlapping. So I changed my memory address to 4 followed by 4 zeros. So I get all the addressing in sequence, or we can actually have gaps in between. That's absolutely fine. But only make sure that you don't overlap the memory spaces. You need to have a distinct memory space. Now, your question might be, you connected lightweight interface. You also connected lightweight interface from here, lightweight AXI master to multi, and that master also was connected to on chip, and you connected to register. And why did not it throw an error? Why only this JTAG threw an error? So what happens is there was a gap in between in the GHRD. Before there was no address in 00 address space. So all the slaves were starting from address 1 followed by 4 zeros. So when I connected my new peripheral, it silently took 0 without throwing an error because that address space was empty. It utilized it, no harm. If I connect another slave, now I have occupied my 0 addressing because QSys by default assigns it as 0 address. Now designer has to go and change that address so that he doesn't make any mistake in by default addressing. So we start with 0. Whenever you add new component, you just have to change the addressing. Now that address is absolutely up to design. It's nothing. It is nothing Cortex specific. It is a design specific requirement. So for now, my register access on both my master interfaces, that is lightweight XE as well as JTAG master, both are on my 00 address space. So that is starting from 00, I go up to 3F. So now remember, this is byte addressing. So that means all the registers are byte addressed. So if you have a 32-bit register, the first address is 0, the next address will be 4 because it's a 4-byte wide. Okay, I'll explain that in the code also because in C code we are going to do the byte addressing. We'll take up that later. Okay, I'll save this. We need to save and we need to generate this. So it will take some time.
Ritesh, can you try something? You can go to tools and there you will have options, and inside options you might have fonts.
Okay, sure. Yeah, I think I'll do that once this generation is completed.
Sure.
Are the fonts really bad?
These are very small. So with tools options, you will be able to choose font size. At least in quarters, that option is there. I'm not sure if that option is there in platform designer.
Okay.
Tools options down there, and then you have fonts. Fonts, messages, fonts down there. Yeah,
Yeah.
here also general fonts, and then messages fonts as well.
Oh, messages fonts. Yeah. Okay. Thank you. Text editor and yeah, in general. Okay. I'll just make it as 50. Messages fonts 15. Text editor 15. Okay. Yeah.
Or Ritesh, do you want to try changing the screen resolution and see if it becomes bigger? Okay.
Yeah.
You'll have to do a bit of scrolling, but that might be one thing which we can try.
Yeah. Sure. We'll try that once this generation completes. Okay. No, not here. Okay. But okay, we'll just finish this and is this okay?
This is much better.
This is better, right? Okay. I think yeah. So I'll continue with my laptop screen, not the monitor screen. Sure. All right. So again, let's recap here. So I have connected lightweight AXI master interface to register HPS FPGA slave, and also a JTAG interface I have connected via this black line here. So you see this slave is connected to two masters. Okay. And the addressing space, yes, here register underscore 0 dot HPS FPGA is on master lightweight master is on 0 addressing space, and JTAG master is on 0 addressing space. Both are 0 0. Right. So two different masters can definitely have same addressing space. They don't overlap because they are two different masters. So in within the masters, you need to have non-overlapping addresses. Okay, so yeah, so we are done with the platform designer now. So I'll just quickly I'll close this, and yeah, I'll have to share the screen again. Yes. So right. Okay. So here you see this is the same screenshot which I have taken. Generate we did, and now we have to do Cortex compilation. So I'll just bring in Cortex here. I just need to since we are not really exporting anything as of now, we don't need to change any file. We don't need to change any thing on this parameter edit or in this instantiation because there are no export signals. But if you have any exported signals, you need to add here. But for this lab, it's okay. I'll just do start compile. I'll be getting all the compilation completed. It will take roughly 10 minutes. So till then, we'll see the other part, the software part. Now, once you, okay, sorry. So once you share, right. So once you save the platform designer, right? So now the platform designer's file extension is .qsys actually. So once you save, this gets all saved in this file. Please don't modify this. I mean, it's a XML format, but you can it's little it's always good to use GUI because you can play around with it. It's quite easy. But if someone wants to, this also can be edited, but not recommended one. So after this QSys, there is a file called SOPC info file. So system underscore, or I would say SOC underscore system dot SOPC info. The same platform designer name file dot SOPC info. So this info file is a kind of a handoff file for us because it gives an address information of all the peripherals which you are connected. So basically it will be PIO, it is your register bank, so all those or all the other peripherals like on-chip memory and all. So all those files are generated or stored here. The addressing details are all stored here. So let the compilation happen. It's just 23%. Here you can see 23% on the right hand bottom corner. So we will actually do a header generation until it's get because we already for header generation we require a SOPC info file which we already have. So we don't need to wait until the compilation finishes. So uh, okay, so what we have to do for this, either you open SOC EDS terminal or you open a NEOS2 command shell. For me, I'm using a NEOS2 command shell. The reason is SOC EDS, this command did not work for me. There's some issue with the installation because I have multiple versions of Cortex installed. There's some environmental variable setting which got missed out from me, which was taking a lot of time. So I just found another way, which is use a NEOS2 command shell. Both performs the same work. So we'll go here. We'll say NEOS2 command shell. And yeah, see, I have two different installations. So I'll just use 20.1 because 20.2 is a pro. So I'll be using 20.1, which is light. And then I'll go to this folder where my SOPC info file is there. So I'll just copy the path. I'll go to say MNT and I'll paste. Just need a forward path because this because this uses a SIGWIN and it uses actually Linux paths. So we need to convert them to forward paths, forward slash, and I think I missed something here. Okay, MNT. Okay, sorry, I again forgot. I'll change this font size. I'll keep it to 20. I will change it to 24. Yeah. So I'm going to the directory where all my files are there. So more important is I need my SOPC info file for now. So this is my SOPC info which I generated, which got generated when I saved my QSys file. I'll just copy this command. Now what it does is it creates a .h file.
Ritesh, there is a question. Linux users, what is the command to be used to invoke the tool?
Okay, SOC, EDS, right?
Yeah.
Okay, yeah. So there's a here you need to go to say go to C FPGA wherever 20.1 with Intel FPGA 20.1 and embedded. So here you'll have a command.sh. So go to this file or in Linux say in Ubuntu, right click, open in terminal this folder, and you run this .sh file. So that will set all the variables for you. Now the question is, where do I find this path? Because there's no C folder in Windows. So you go to your installation directory where your SOC EDS is installed. So okay, just other than C, this path will be common. Intel FPGA / 20.1 / embedded. So you just have to go there, and or another way to look into this is, okay, give me one minute. So go to rocket boards. We have shared one path. Yeah, so I shared this link before. So in Linux, right? Yes, install. So once you install, you'll actually see where it got installed. So in this, yeah, so here, so this is your path. So Intel FPGA 20.1. So this is the folder which you need to access.
Or you can just do a grep and then you can find where that embedded shell is sitting.
Yes, that is one idea. Okay. All right. So I'll just delete the .h file which was generated before. So rm hps_0.h. I deleted this. There's no .h file. Now, yeah, as I said, I'll copy this command and I'll just run. So this actually this converts. If you see, it converted generated a hps_0.h file. So I'll go to this folder and I'll find for my HPS folder. Yes, here hps_0_h .h. That's a header file. So I generated a header file based on my QSys. So or SOPC info file. Now this contains all the addressing or address maps of the FPGA side peripherals. If you see this contains all the information, and these are the two masters. And if you see on-chip memory is there, so this is for on-chip memory. Then this is for register, as you said, You know, we in QSys we saw 0x00 address, and then we had a system ID which was on 1000, like that. So LED PIO was on 10040. I mean the base addresses. So you'll see all the base addresses here. And register for us, we need this register underscore 0 underscore base. So this, and span is actually is like maximum. What is the address size of this? And the end address is 3. So you'll find the details for all of them. So for button PIO and LED PIO, yeah, LED PIO, all the information required to access. So all peripherals connected to the these two masters, we get information of those. Now I will use this macros which are defined in my hex file, header file, sorry, which are defined in my header file to include it in my C code and then compile my C code. That way, I don't need to really, in a complex subsystem, I don't need to worry about all the addressing which I do. Just hardware engineer can define his addressing. He will give me this SOPC info file. I will generate my header and I will start coding my C. I don't need to worry tomorrow if someone changes that address. I'll just follow the same steps, and these steps can be automated through TCL. So I don't need to worry that it's like you don't need to blame a hardware engineer later that you changed the address without letting me know. So that's something one use I found with this kind of setup. Okay, so yeah, so we are done with Neos to terminal, so we can close it. We don't need it now. We'll go to this. Okay. Meanwhile, before we start writing C code, or we'll see C code, and yes, so in 10 minutes we have just completed the compilation, 100% completed. So now, if we see the folder, we should have a .sof file. So we have a .sof file. So we have one .sof file, and then if you see here HPS underscore ISW underscore handoff file. So even this gets generated. So here, you see here, it's today's date, it got updated. So just keep a eye on when the folder got updated, because you don't want the stale data to be carry forwarded. Because few changes are always done in the system. You don't want your old design or the GHRD design to be carry forwarded, and later you debug like where the things went wrong. So these are all the files required for your U-boot generation. This is the handoff files. As of now, we don't need it as of now because we are using the SD card image, which is part of the GSRD. So we'll go back, and okay, now on the C part. So we'll go back one step back. So HPS underscore code is my folder where I have kept all my C code and my hex file. So I'll just copy this file, the .h, the header file which got recently generated, and I'll just paste. The reason is like I don't want to really have the wrong addressing again. So I just need to make sure that whatever I change addressing now is reflecting in my C code. So I'll open my C code. You will see the C code in the drive. So yeah, so it contains the main. So basically, main is your starting point, and we have declared a virtual base here, and it's a point, and where you'll actually memory map your base address or hardware addresses here, and basically you'll reserve memory in your Linux for the memory map addresses. So a Linux kernel reserves some part of the memory for all the IOs which are there in its system. So we're trying to just memory map them. Uh, your bridge is also part of those memory map. And then we have LED. Again, I just took this code as a base reference from the GHRD. I will show from where it is uh, so that even you can start taking up from there. In the demonstration, SOC FPGA, my first FPGA HPS and C code. So you can always take from here. Even the same folder is here. But for this lab, I would say you anyway, this is shared in the drive, so you can actually take it from here also. So this is also your base code to start with. So I'm just going to control my LED from my base address to the LED plus the lightweight, because it is mapped to the lightweight FPGA slave. And then I'm adding the base address of the LED, so that this completely makes my address where my LED is situated. And similarly, this reg 0, reg 1, reg 2, and reg 3 are my addresses actually, where my actual registers are mapped. My FPGA registers are mapped to this address. Now, what I do is I actually write using memory mapped interface. So I actually write some values to this to my address. So where this value goes and does a Avalon memory map transactions to my FPGA. So I'm writing 0000123, some hex number. It's a 32-bit integer, so I just convert it to hex, and so these values I'm just trying to load it to my registers. And this is a simple program where I'm just trying to toggle the LEDs sequentially from left to right. It just keeps uh, keeps blinking the LEDs from left to right in a sequence of I think 100 milliseconds of time frame. And it does for 60 seconds, and then it comes out. This loop comes out. So this is a very simple C code. And then on using this, and you can start accessing your DDR memory. You can add code. Eventually, you can add all the code required to access. You can do a DMA from memory to FPGA, or kind of a burst transactions from FPGA to HPS. So a lot of things can sit into this C code. Okay, so now we'll do the make file. So we'll go to this folder or this path. Again, I need to change the slash. Okay, now I have my code, and just I'll explain a little bit about the make file. So again, the make file here is it's a simple make file. First, I set up all my I set up a target. What is my module name? I am saying reg access. So this will be my output name basically. So and then I'll be this is what is that Altera device family SOC Cyclone 5 area 5, and this is my root directory. So where my SOC EDC is installed. So and then it is pointing to hardware libs. So I'm giving the path of the hardware libs, which cross compiler I'm using. So this is one of the important. I'm using ARM Linux GNU EABI hard floating point uh, cross compiler. Again, this cross compiler adds up GCC, so it becomes ARM Linux GNU EABI HF GCC. It uses the same GCC which we installed before, and then it converts to output file and then converts to the executable file. So yeah, so again, there are two arguments you can actually make, and you can do a make clean. So So I'll just do a make clean so that all my intermediate files are cleared and even my previous generated files are cleared. Okay, so I just do make, and you'll see a file called reg access here. So this is something we need to copy now to the board. Yeah. So I'll this is created. So if you see the timestamp, it is like today's date and 2 o'clock. So I'll just take this and I will copy it to the SD card. Just make sure that we don't touch these two files. This is very important because this is U-boot and device tree blobs. We're not touching this. We're not interfering with this. Otherwise, the SD card will not boot up, or your ARM will never boot up with this SD card. So I'll just I'll just create a folder called shared because I don't want to disturb those other two files. So again, so this you will see that there is only one drive which I got because my SD card is 16 GB, but it's just showing 870 MB because this drive is a FAT32. So Windows can find FAT or recognize FAT32 file system, while the other file systems are not there. So you don't need to worry about them. That's where these things are there. If I can access my Linux root file system, I can just paste in my home directory itself or my user folder, which is there. But that's not possible, so I'm just putting it to the FAT32 file system. And I'll show you the steps where I can access the FAT32 file systems from Linux as well. So we can copy this file and we can execute it. Okay. So now now we have, as we discussed, now we have the Cortex programming ready. SOF file is ready. Now we have the C code ready, and also the regex, one of the binary also ready to run the C code. What next? So we did preparing SD card also. I took this first, so just which we can do. We did it using Win32 disk imager, and now it's time to power on the board. Just I'll just insert the SD card to the slot in the board, and I will power on. Now, as I discussed in one of the slide, I'll just again present that slide. Yeah, so this is my setup. This is my setup where, okay, I'm sorry for all the, okay. So this is my setup where I'm having, I'm trying to presentation mode so that everyone can see. I don't see that happening.
It's going to the presenter's view. Probably you'll have to share the other screen.
Okay. Yeah, here. Right. So here I have a serial terminal, and I'll be running serial terminal on host. I have connected my USB to the UART and a JTAG to my JTAG or a USB cable to my JTAG pin. But this is just a USB cable actually, USB micro USB cable. Okay, so okay, Okay. Okay. Now I have powered on the board, and I'll be connecting my board to the putty, that is terminal. I need to change my baud rate to 115200, and you need to find the COM port which is it's taken. Mine is COM8. Hopefully it's the same. Yes, so it's the same, and it's connected. So it's showing me FPGA login. I'll just increase the font size here also. Yeah. So I'll by default the root password, the login is root, and there is no password. If you see there will be anything, it will be blank. You don't see any files. The root, you will be in home slash home slash root. So now what we need to do is we powered on. Okay. So we'll also load the FPGA binary. We'll complete that first. So go to tools and Cortex programmer. Also, there is a shortcut here. Any one of them should work. Okay. Select tools, programmer. Select tool programmer. Then you will open. You'll see something like this. Okay. You need to do auto edit. Then you'll find some device options here. Select. Actually, you can select anyone, or you can select the closest to it. Anyway, it will ask for auto detect does not match the programmer device list because you choose any one of them. So you can say yes, because once you load the binary, it will actually select the proper one. So right click, change file. You'll find a window to load the file, the SOF file. So same here, the option is to program or configure. Select it and start, and it should show 100% success. So we're done with the programming. So the same steps are shown here in the document as well. We'll go next. Yeah, and then accessing your terminal, we did that. We connected to root. Now, only thing now is how do we transfer the executor for files? Because we copied it in the FAT32 partition. So because you'll not find it in here. You won't find that shared folder here. So how do you do? So there is a process to load FAT32 system or mount FAT32 file systems. So just do fdisk. You'll find 3 partitions. So here, if you see, you get a FAT32 Windows 95 FAT32 file system. So I have provided the commands here, fdisk-l, and then you just will do a make direct. We'll just create a directory called D in the mount path, and we'll just mount the device and we'll just specify the name of the partition here. The name of the partition is dev/mmc-0p1 0p1. This is mine. So this is complete. So now what I'll do, I'll go to this path /mount /d. So now all the files are available here. Just make sure that don't touch these two files again, DTB and ZImage. But I see my shared folder here. So I have my reg access. I'll just copy this reg access. Oops. I'll go to home, root, and or I can actually create a folder also. I copied it in my root file. I can actually create a folder here also, that is registers, and I'll just say move this file to registers. Yeah, and now I can actually start running this code. Before that, I just want to show, are we doing this properly? We need to confirm it, right? So we are going to use, does my architecture work? How do I make sure that whatever I am writing a code here, well, I wrote a code on main file or main.c. I'm going to run this, and how do I make sure that my register are going to get updated? Just a recap, we have written this code, which is I'm loading 1, 2, 3, 4, 5, 6, 7, 8, A, B, C, D, and then some 1, 2, 3, 4, 5, 6, 7. So these values I'm writing to 4 registers. So how do I make sure I read? I write properly. So first on my laptop, through Cortex system console, I'm going to read this all registers. So that is provided in my system console script regaccess.tcl. If I open here, I have actually a register base address, which is 400. I think it has to be changed now. I have made it as 0. This is important. Just to confirm that, again, I can go back to my hex file, and this should be 0. So yeah, so I have made it as 0. So here, reg 0, reg 1, reg 2, and this is 048C. Remember, your C code also you have added here 048C. So again, as I said, these are byte addressing. So each of your register addressed through bytes. So 4 byte makes 32 bit. So 4 bytes, so 0, 1, 2, 3 makes up 132 bit. Then next is 4. If I have to show it in another, so it's like this. This is a register bank, like this. 1, 2, 3, and 4. So okay, let's start from 0. So this is my 0x0. This is 32-bit wide, 32-bit wide, and ARM. This ARM is an Little Indian. So your 0th nibble or LSB sits in 0th byte. So 0. So it is like this. So 3, 2. Sorry, it's like this. 1. Okay. Now again, this is not to scale, but yeah, something like this. Yeah. So 0, 1, 2, 3, and the next byte should start at 0x04, like that. So it goes like this. So I would copy and put it here, and then next is 7, 6, 5, and 4. So this is how it goes. So this is 32 bits. So these are all 4 bytes, like that. So we are going to access all of these registers from byte addressing. So even in my tickle file, I have addressed them as byte addressing. base address plus the offset address. Then I will start JTAG service master using this API stop service master, but you don't need to worry about this. This is all command line for system console. I will read this from my red 0 address. So red 0 address I read, and I'll display it as red 0, red 1, red 2, red 3. That's all. I'm reading using master read 32 API, which is part of our system console API documentation. So quickly, first what I want to do is I want to check what are my values before even starting my C code or before executing my C code. So I'm going to open my system console in tools, system debug tools, system console. So it will take some time to initialize the JTAG and all. So I'll just see which path I am into. So I'm in D1 SOC GHRD, but I need to go to this folder. Okay, I need to go one step back and this folder. Oops, it doesn't allow ls. So in this, I'm going to run this. I'm going to execute this tickle file. So access regaccess.tcl. See, all the registers are 0. One of the reason why they are 0 is to do with my VHDL file, because if you see my read data value on reset, I have made it as 0. So by default on reset, because my FPGA goes to reset after the power on, this register sets at to 0. So you are seeing this value at this point of time. Now let us run this code, regaccess code. So it goes, and on my board, I'm seeing LED going, toggling, because there's a LED toggle code also. And also, let us see if I can access these registers. So this is my registers. So I don't think I can change my, okay. So I don't have, I cannot change my screen or font size here, but I'm just saying out reg 0 is 1, 2, 3, 4, and reg 1 is 5, 6, 7, 8. This is all a little Indian format which I'm reading out. So that means that my architecture is working well now. So whatever I wrote a C file, I triggered a C file and I wrote values from here. It all way traveled from that. Those data went through L3 slave peripheral switch to lightweight H2F bridge to my IP. And in my IP, my write port is working well because it has written the data into red 0, 1, 2, 3, 4 well. And in my JTAG, I'm reading this value. So my read port also is working well. So my IP is, overall my IP is in good shape, I would say. So that's the end of this lab. So this is how you will see. I'm sorry. Yeah, this is how you will see the result when you run the tickle file. All this, yeah. So this tutorial is there in the drive. So feel free to run this when you get a chance to access the board. Yeah. Okay, and I think, yeah. So we okay. This is just an example code for main program. How do you start SOCDS? Yeah. So this is converted. Yeah, this is the reference documentation. So you can find all the SOC FPGAs related information here. Cyclone 5 SOC information here, and embedded development suite user guide, and rocketboards.org link directly here, and all the development kits you can find it here. Training links, few important training links I have shared here. The same things. I think there are few trainings which are same to the prerequisites which are given in the schedule. Contact information, yeah. Feel free to reach out to Vikas and me for any queries. And I would call out as the end of this session for today. Firoz-ji?
So Ritesh, we don't have any further questions.
Yeah.
Right. Firoz-ji?
Yes, sir. Good afternoon, sir. Yeah.
So yeah, I think over to you.
Yes, sir. Sir, I think so. All the questions are already been addressed. There is only one question, I think so, to invoke NIOS 2.
Yeah. So
I think that's already answered.
Yeah, okay.
No, that's
Okay,
already
sir.
answered. Yeah.
Okay, so sir, I think so we are okay, we have completed all the topics for today, and I thank you Ritesh sir, thank you Vikas sir, and thank you Puneet sir also. You were also connected throughout the session, so thanks a lot. And I think so there is a question sir right now for a VLSI design engineer, which programming language we must focus on.
I'll take the question.
sure,
Yeah.
sure.
Probably VLSI engineer, what I would really recommend everyone is, programming language is the second priority. I would say please concentrate on the fundamentals. It could be Verilog, it could be VHDL, but in industry, a lot of people are using Verilog, right? But again, a lot of defense sector uses VHDL. So if your fundamentals are strong, it really doesn't matter whether it is VHDL or Verilog.
Sir, which part of this project we must focus on? Okay, sorry, sir. Yeah, it has already been. Right. So, sir, I think so. There is no more questions. So, thank you, sir, for joining with us. And hopefully, sir, you will be also joining during the validatory session also. So with this, we would like to end today's session. I request all the participants to please go through the instruction. We are again and again making this announcement because every time there is some kind of issues that you all face. So the quiz is from 2:45 to 3:15. At 3:15, the link will be closed. I request you all to please submit your answer before 3:15. Don't wait till 3:15. So it is a repeated announcement. 10 minutes grace time is also given to all of you. I request you all to please connect at 2:45 and complete your MCQ before 3:15. So thanks a lot, Vikas sir. Thanks a lot, Ritesh sir, and thank you, Puneet sir. So with this, we will conclude today's session.
Thanks to all the participants and thanks to the organizers.
Thank you, sir.
Thank you, everyone. Thanks, participants, and see you on day 10,
10, sir.
24th.
Yes, sir. Yes, sir. Thank you, sir. Thanks a lot, sir.